Okay, I guess you can all see.
Yes, we can see.
Okay, great, thank you. So good morning again, welcome. Today we will have a workshop organized by RUZGEM, METU Wind Energy Research Center, and EuroCC at Turkey project team, together with the help of ULAKBİM Truba, HPC center, let's say, national center. So today we will be talking about wind energy computational analysis, mostly what we have been doing, and we will try to actually try to introduce basic terminology and concepts. If you are new to this area, hopefully you will find it helpful. If you are already familiar with this kind of computational analysis, you may still enjoy some sample applications and what we have been doing at RUZGEM in METU. If you have questions, we will try to answer at the end of each session, each presentations. So you can write into Q&A, and we can go over them after the presentations. Okay, so just a second. So let me continue. So today we will have actually 3 topics: aerodynamic analysis, design analysis, and wind farm analysis. As you can see the timeline here, for each of these kind of analysis, we will also be showing applications by using open software, open CFD software such as SU2 and OpenFOAM, and also aerodynamic analysis software OpenFast. The outline is, as you can see, we will start with the introduction to wind turbine aerodynamics, so you will get familiar with the terminology, and then we will start showing applications for airfoil CFD simulations and rotor CFD simulations. And in the afternoon, we will talk about offshore wind turbine design, introduction to the wind turbines, offshore wind turbines, and application by using OpenFast. And then we will also talk about the wake models and wind farm analysis, and again, applications using OpenFOAM. What we are, so I will first introduce, before I start the first presentation, I will introduce our project and also RUZGEM a little bit. So my name is Nilay Sezer Uzol. I'm an associate professor at the Department of Aerospace Engineering in METU. Just a second. Okay. Also, Associate Professor Dr. Elif Oğuz from Civil Engineering Department from METU will help us in the afternoon. And we are both working on wind energy and at RUZGEM together. And we also have our students, mostly PhD candidates, senior research assistants, helping out with the presentations today. You can see some important web pages here. So after this workshop, you will be able to reach this presentation, so you can go over for more information as well. With this project, EuroCC at Turkey project, as a METU CFD group especially, we have been doing several trainings in the last 2 years of this project. The project will be completed at the end of this year, but there will be a second phase starting. So we'll continue with this kind of trainings in the next year as well, probably. The aim is to help especially the SMEs, small companies who needs to use the HPC systems and CFD, especially for our group, in their projects, what they want to learn, they are not familiar with. So we are trying to help them through these trainings and also through the test cases, actually. And you can see also we developed documentations related to HPC and CFD, and you can find them in docstruba.gov.tr website. We have been doing several, so who are we? We have been doing research or studying, doing projects in these areas, basically aerodynamic simulations and design, wind energy, wind turbines, wind farms, combustion, turbulence, numerical methods, linear algebra, parallel programming, and CFD software development using parallel libraries. And we have been doing collaborations with industry through our PhD studies, MS studies, and also collaborative projects with the industry or other universities. And as I said, with this project, EuroCC at Turkey project, we have been doing test cases for SMEs as well. So who are we at RUZGEM also at the same time? So METU RUZGEM Wind Energy Research Center at METU, established in 2011 with 9 million euros research infrastructure grant from the Ministry of Development. It was a collaborative effort of 9 different METU departments, and we have been doing national and international research projects, industry works, and thesis studies and training activities related to wind energy at the center. Here, this center has 4 main laboratories, which was established through this grant, and basically the biggest one is the experimental aerodynamic facility. Big wind tunnel was established. Together with that, we have been doing computational aerodynamic studies, structures and materials laboratories, experimental and computational electromechanics laboratory, and high performance computing laboratory as well. For training, we have been using them in our department as well in the graduate courses. So related with the center, there are more than 25 faculty members from 6 different METU departments actively working on wind energy related projects. And there have been more than 35 graduate students so far working in this area. And we are also a member of the European Academy of Wind Energy. As I said, we have this big facility, big wind tunnel established through this project. And here we have been doing, it started working in the last 2 years, providing tests for the industry and also research projects, both aerospace related, civil engineering related, and also wind energy related projects and tests has been done in this facility. And you can also see other facilities, structural laboratories, and other wind tunnels and open test section, wind turbine tests. You can see some sample pictures here. There have been several projects, as you can see here, some of them, some sample projects, airfoil testings together with Siemens Gamesa, wind turbine wakes studies, experimental studies, with many European universities and centers together, and also another project with Denmark, Wind Flag has been going on already, and European Wind Atlas project we have contributed to these projects as well as a center. So let me start with today's workshop. First, I will present introduction to wind turbine aerodynamics. Okay, so I would like to talk here a little bit about wind energy and wind turbine aerodynamics and aerodynamic analysis methodologies. Also a little bit about CFD and the softwares that we are planning to talk about today. SU2, OpenFOAM, and OpenFast. I will introduce briefly those software as well. Okay, so what are wind turbines? As most of you know, in Turkey, we are familiar with horizontal axis wind turbines, mostly onshore wind turbines, and the number of turbines and the wind energy contribution, renewable energy contribution has been increasing in the recent years. But if we classify them, we can see that wind turbines can be horizontal axis wind turbines, hafts, or vertical axis wind turbines rotating around the vertical axis, wafts. And also we mostly see them in together as you can see here in wind farms, onshore wind farms or offshore wind farms. And this is the most famous picture that you can see the wakes interacting in a wind farm, offshore wind farm. And recent years, floating offshore wind turbines becoming popular. And today we'll be also talking about Dr. Elif Oğuz will be talking about those in the afternoon. And we will show some example studies as well. Okay, so what are rotary wings? In general, rotating wings, rotating blades, we can see them in helicopters, wind turbines, propellers, right? All of them actually, if you can see here, a classical wing will have a tip vortices, right? So an aircraft, at the tip of the wings, we will see these tip vortices going downstream, shedding downstream. But in the rotating wing cases, rotating blades, when we have rotating blades, these tip vortices remain close to the rotor blades. In the helicopter, remain close to the fuselage, and in the wind farms, for the wind turbines, these tip vortices shed behind and interact with the next turbine in a wind farm. As you can see here, these are all three-dimensional flow problems. And most of the time they're unsteady, and we see flow separation, separated flows, and vertical flows, so vertical structures in the wake behind the rotors, and also turbulence we see in this kind of flow fields. So a rotor flow itself is a complex flow, but they also, for example, here you can see a horizontal axis wind turbine rotor, test rotor. It is on top of a tower, right? So it is interacting, this flow field interacting with this tower as well. So there are some complex interactions, rotor interactions in wind farms, as you can see here in this picture, many number of rotors behind each other, and the wakes are interacting, hitting to the next rotor. So there are complex interactions in wind farms. So rotor-tower interactions, rotor-rotor interactions, and also atmospheric boundary conditions. Atmospheric wind is coming in a boundary layer, atmospheric boundary layer, hitting to this wind turbine and interacting with the flow of the turbine. So there are interactions of the rotor with these atmospheric boundary layers and atmospheric turbulence as well. So therefore, a complex flow problems and accurate computations of these kind of rotary wing flow field problems are really challenging and expensive, and they need high performance computing. As I said, so these wake of the rotors, they interact, with these interactions, they generate complex inflow conditions for the downstream turbine. Presence of the atmospheric wind shear, turbulence, and also gas yaw upstream turbines. So the wind may not be coming straight directly to the rotor, perpendicular to the rotor, but it may be coming in a yaw condition at an angle, and interactions with the tower wakes add complexity, more complexity to the flows. What is the result? Because of these complex flows, we will see significant reductions in the mean power and thrust levels for these systems. High unsteady inflow could also generate violent fluctuations in the torque and thrust levels and the loads, aerodynamic loads, and this may cause structural damage to the turbine blades as well. So what we do to investigate these kind of complex flow fields or to design a system, such a complex system, we can use some aerodynamic modeling tools such as engineering models, simplified models, or a little bit advanced vortex methods, lifting line, vortex lattice, surface panels, Fourier prescribed wake or vortex particle methods recently becoming popular, and also computational fluid dynamics methods using actuator disk, actuator line, or full runs, U-runs, LES type simulations. I will explain this in this presentation actually. So if you are not familiar, don't worry about them right now. Okay, so let's see. Today we will be talking about computational aerodynamic analysis mostly. But when we look at the aerodynamic approaches, we actually see three approaches, okay? Theoretical approach, experimental, and computational. Theoretical models, simplified engineering models may have some simple calculations, to do some simple calculations to estimate the power levels of the wind turbines, okay? So this is our aim, to obtain the power, so we can design better wind turbines to obtain more power from the wind. So we will not be talking about these first two, but here computational tools for the aerodynamic calculations. So simple engineering models can consist of momentum theory, blade element theory, and a combination of these two, blade element momentum theory. Vortex methods, as I said in the previous slide as well, panel or vortex methods, which may include free wake calculations. So these will be more accurate compared to the simple models, because they include more physics, more complex flow characteristics into the solution. But if you go from the simple to the advanced methodologies, you will see the computational fluid dynamics, CFD, which can have runs, Reynolds average Navier-Stokes simulations, large eddy simulations, and together with modeling the rotor with this kind of approaches, which is using actually these simple engineering models. So based on this momentum theory actuator disk model or blade element theory actuator line model can be hybridly combined with the CFD simulations. So let's see them one by one, so you get familiar with the terminology here. So because you'll see applications in the next presentations. Momentum theory is the basic theory. It's the ideal theory, actually. We are assuming an ideal rotor. So that means there are no losses, no non-ideal conditions. So everything is the perfect ideal conditions. And this theory gives you the most power that you can extract from the wind by using a wind turbine rotor, okay? So it helps to calculate this extracting energy from the air passing through the disk by assuming an actuator disk instead of a rotor, real rotor geometry, rotor blades. We just assume a disk, circular disk, and through this disk we have the stream tube expanding, because we are extracting the energy, kinetic energy, so velocity is decreasing. As a result, conservation of mass, we are seeing an expanding stream tube. By using the conservation of momentum, we can obtain the thrust that's created at this actuator disk through this pressure difference, okay? So the flow is going through this disk in this stream tube, and we have this pressure difference, which results in a thrust. And if you multiply this thrust with the velocity, what you obtain is the power, actually, right? So power, from the definition of power, thrust times the velocity at the disk will give you the power. So momentum theory actually gives us, with these simplified assumptions and using the equations of motion, conservation of mass, conservation of momentum, and conservation of energy. So we obtain how much velocity is decreasing. So we can estimate that. Okay, so this is called induced velocity. So we are decreasing A times U1 free stream velocity through this theory, okay? And we create this much thrust at the rotor disk, and this is the wake velocity. So velocity is decreasing 2 times v. Okay, so momentum theory actually gives us that there's an induced velocity at the rotor disk v, and in the wake it is 2 times v. And this A is called the induction or inflow factor. That's the unknown parameter that we are trying to estimate correctly, actually. So if we can find A, we can estimate thrust, and we can estimate power through momentum theory. So if we have power, we can calculate power coefficient, and momentum theory tells us that there's a limit, it's called Betz limit. It is 59.3% of the wind energy, wind power you can extract through this wind turbine system. So we have this power coefficient distribution, and this is the Betz limit here, okay, and this is the thrust coefficient distribution. Here also, since the thrust coefficient in reality valid up to here, and then we need some empirical relations for the realistic estimations, because momentum theory works in this state up to this value here, induction factor. After that, we have turbulent wake state. It's more complex, complicated state, so we can estimate that through experiments or more realistic calculations. Okay, so what we have seen here, there's a power curve, okay? This is the typical curve for wind turbine rotors, which shows the wind turbine performance, okay? So for a given wind speed, this rotor extracts this much power, okay? So for each wind speed, let's say 12 meters per second, this is 120 kilowatts of power you can get from the wind. So this is a classical power curve, and the maximum here is called the rated power. Minimum power that you start to get at the cut-in wind speed, and the maximum power that you get at the cut-out wind speed. After this, it becomes dangerous, so you just brake the turbines, apply the brakes and not use the turbines for these high wind conditions. So there's a regular wind conditions that this turbine provides us a power, okay, power curve. So through the applications today, we will see some estimations of the power curves and through different analysis, trying to estimate this power curve accurately so that we can design or we can estimate the wind power that we can obtain, okay? And after this, some maximum wind speed and maximum power, we can actually also apply control systems. So naturally, the blades, after some high speeds, they cannot generate enough torque or thrust. So they stall, basically, or airfoils will stall. So if you can change the pitch angle of attack of the airfoils, you can have pitch regulated turbines, so you can continue to obtain this maximum power at this high speed as well by applying control strategies. Okay, so momentum theory assumed actuator disk. We didn't know anything about the details of the blade geometry. In blade element theory, and together with the momentum theory, it's called blade element momentum theory, they both need to give us the same estimation of thrust and torque and power. So in the blade element theory, we actually know the blade geometry. So this is our blade from root to tip. We have airfoil distribution, we have chord length distribution, we have twist distribution. And for each blade element, if we cut this blade into 10 elements, let's say, so for each section, we know the airfoil section, and we know the relative velocities coming towards this section, and we can calculate the lift and drag aerodynamic forces applied to this airfoil through the flow, through the wind flowing over this airfoil. So we have the lift and drag or normal and tangential forces. When we integrate them, we can obtain the thrust and torque values actually. So if we have the thrust from the blade element theory and thrust from the momentum theory, we should expect to have the same thrust estimation. So from there, we can estimate the induced velocity, inflow factor, induced velocity factor, or induction factor A. That's the unknown, if you remember. So this is called BAM theory. Similarly, there's this axial induction and also rotational induction, A prime. So these are two unknowns that we are trying to solve through BAM theories or BAM analysis, blade element analysis. So what we have during the design of the rotor blades, we start with the airfoil selections, rotor geometry. For these airfoil selections, we need aerodynamic characteristics of the airfoils, CL, lift coefficient, and CD, drag coefficient, drag polars. So airfoil polars, we call them actually. So we use them in the BAM theory. For each section of the blade, these airfoils will see some relative angle of attacks, relative velocities, right? So this is relative velocity, relative angle of attack, alpha. So this is how this airfoil will generate lift and drag. So we can integrate them and find the total loads, aerodynamic loads, thrust, and power. We can also perform aeroelastic analysis, or we can also do design and optimization studies, airfoil design or rotor blade geometry design, how the chord length will change, how the twist will change, so how the airfoils should be placed along the blade. So this is called optimization, design and optimization of the rotor. So in this kind of design cycles, let's say, we can use BAM theory, yes. We can also use panel methods for detailed analysis, or we can use CFD, and we can do optimization, and then we can continue for more detailed design and analysis. So after this simplified theories, momentum theory and blade element theory, I would like to talk about vortex panel methods with free wake modeling. Here we have been developing and using Aerosim code, panel code. It's a 3D unsteady free wake vortex panel method code. We can actually model any number of combination of rotors, wings, and other non-lifting bodies. What we do here, we take the blades. Let's say here we have two-bladed NRAL rotor test case. We have the surface panels on the blades and also in the wake, in the flow field, which is free to move. So this is how it's called free wake method actually. And these rotor blades rotate or they can do any 4D motion actually. They can flap, pitch, lead lag also. So we can also simulate helicopter rotors or propellers as well. In this model, we are using the Biot-Savart law actually. And for that law, you need to model. So we have these vortex panels. And for these vortex panels, we need to model the core of the vortices, vortex lines. And there are different kinds of models available that we can use. And we can also consider vortex core expansion or stretching for more accurate computations. Here are some examples from our previous studies for NRAL phase 6 rotor test model. You can see the tip vortex only or whole wake shedding behind the rotor as it rotates. So it's an unsteady computational approach. Another study, for example, here we have the atmospheric boundary layer coming towards the rotor. So the velocity, the wind is not coming same magnitude to all of the blade locations as they rotate. Actually, at the top, it can see high velocities. At the below positions, it can see lower velocities because being in the atmospheric boundary layer near the ground, lower velocities. So you see the wake is stretching and interacting and getting more complicated skewed shape. So it's not symmetrical like here, but unsymmetrical wake shape. As a result, we can also apply, in this study, I think we applied a gust condition. So the wind velocity is increasing and decreasing, so it's changing in magnitude as well. So what we see here, the thrust, instead of having this straight, smooth thrust value, we have these oscillations, right? In different wind conditions, in the normal wind conditions, you have small oscillations, but if you have gust extreme wind conditions, you might see these extreme oscillations in the thrust, which will result in more aeroelastic behavior and more loads on the blade structure as well. So, or also power generation will fluctuate, and this will cause fluctuations in the electricity generation as well. Another test case, blind test cases of NTNU with 3 blades, a 3-bladed rotor model, 1 blade and 1 rotor here and 2 rotors here interacting with each other. As you can see, the symmetrical rotor wake hitting downstream rotor, interacting, the wakes of both rotors interacting, and you see a more complicated wake shape. So as a result, instead of having this nice smooth thrust value, downstream rotor in this complex wake, we'll see oscillating and lower thrust values or torque values as well. So power generation will be lower for the downstream rotors. Another simulation case using CFD here, using overset grids with CFD++ code. We have the full rotor geometry, as you can see. The rotors are skewed a little bit, so the wake of this front rotor hitting half of the wake of the downstream rotor and interacting, as you can see here. And this is another vertical vorticity magnitude contour plots that we try to investigate the wake shapes and wake characteristics so that we can estimate the power generation in wind farms. So we will be talking about wind farms and wake models in the afternoon today. For more detailed CFD analysis, you can actually do unsteady CFD computations, and you can get, for example, here, a normal wind condition, a low wind, 7 meters per second. Here, 15 meters per second, high wind condition. So you start to see flow separations, more vertical structures in the wake. Here, the wind is coming at an angle, so it's a yaw wind condition. So in this case, the wake is not symmetrical, but it is skewed, as you can see. And so it may be hitting not the rotor behind, but maybe at an angle, hitting the other downstream rotors as well. So together with CFD or computational analysis, validations are also important. So we also do at RUZGEM, we do experimental studies. Some of the examples here, some wind turbine, rotor blade, winglet design, winglet experimental measurements, rotor tests, rotor model tests in the open test sections, and some PIV measurements for validations that has been done before. Okay, so after seeing the sample solutions, I would like to talk about CFD a little bit. If you are new to CFD or if you like to learn, so this will give you a start for terminology again. So what is CFD, computational fluid dynamics? So in general, fluid dynamics problems, any geometry in a flow field will be governed by the fluid dynamics equations, right? So most general equations are Boltzmann equations. For the rarefied gas dynamics, they have been used, but in the recent years now, molecular dynamic approaches, with the advancements of the computers now, we can also use for normal flow, viscous flow conditions as well. We start to see those approaches. So if you start with the Boltzmann equations, if you assume continuum approach, you get the Navier-Stokes equations. If you assume implicit approach, you get Euler equations. if you assume irrotational flow, you will end up with the full potential equation. So we can solve vortex methods, for example, using the potential flow governing equation. If we linearize them, we can get Prandtl-Goulart wave equation. If we also assume incompressible flow, Laplace equation again for potential flows. So instead of having the rarefied, we can have continuum flow, viscous effects, rotational effects, nonlinear effects, compressible effects, or all continuum approach in the equation. So we need to know our problem, fluid flow, which is the best, which can be used for our problem. So you need to be aware of the assumptions as well, so that you can select the correct methodology or solution approach for your problem. So what are the simulation steps in CFD? First, we do some pre-processing. So we have our blade geometry, right? We designed our rotor blade. It is three-bladed rotor. So we have a rotor and a grid generated around this rotor. So we have a computational domain generation. And inside this computational domain, we need to generate our grids. That means grid cells. So we divide this domain into small cells so that we can calculate the governing equations of fluid flow in each cell, actually. For this computational domain, most of the time, since we are using for complex flow problems, we need to use high performance computing. So we need to divide this domain into number of processors that we need to use. So we need to do grid partitioning as well. So pre-processing includes solid modeling, grid generation, and grid partitioning. So after we have a grid ready, being ready, so we can start our computation. For this, we need a flow solver, CFD flow solver, which solves the governing flow equations using numerical methods and turbulence modeling, and obtain as a result after these computations, again in high performance computing on HPC systems using parallel programming with message passing libraries between the processors. So we can obtain the flow field. What is flow field? Calculation of the flow variables. We need to calculate at each cell, at each grid point, we will be able to calculate velocity, pressure, temperature, density, so basic flow variables. After obtaining this flow variable, what we need to do post-processing, because our aim is to obtain or to estimate the thrust or power integrated quantities, right? So we need to do some calculation of forces and moments. We need to visualize the flow field so we can understand what's going on, what can be the problems related to our design, so we can try to improve our design, okay? So pre-processing, computation, and post-processing are the main steps for CFD simulations. Well, today, actually, pre-processing still takes most of the time. CFD simulations on HPC systems may take hours of simulations, days of simulations, or months of simulations, depending on the problem and your needs of accuracy. And post-processing, also with the experienced users, it will also take time to obtain the useful results from your calculations. Okay, so let's look at these steps. So grid generation and visualization, we will not talk about them today. We have talked about them in the previous trainings a little bit. Maybe in the future we can have more discussions on that. For numerical methods, we will not talk in detail, but you will see applications and some terminology that's being used in the simulations. So I will just summarize them here. We have these governing equations for our problem with the assumptions that we have made. So implicit Euler equations if we need to solve, this is our mathematical model. How we can solve Euler equations, which numerical model method we can use. We can use finite difference methods, finite volume methods, finite element, or spectral or meshless methods. So this is called discretization approaches. And this way we obtain our numerical model. So mathematical model can have some errors in itself. Numerical model can have some errors in itself, right? After that, for this numerical method, with the approaches that we selected, we can choose the correct numerical algorithms or methods. Time integration methods for unsteady problems. So we are approximately solving our governing equations using these numerical methods. Iteration methods, steady state problems. Flux calculation schemes also important, using finite difference or finite volume. And also boundary conditions. What are the suitable boundary conditions for your numerical model? Okay, wall conditions, far field conditions, any inflow conditions, gust conditions, or any flow control strategies that you need to apply. So boundary conditions become important as well. So grid generation, you need to create your grid before starting the computations and discretize your domain, computational domain. And after you compute and obtain the solution, flow field solution, you can visualize and try to get meaningful results such as thrust, torque, power values, or flow field characteristics, wake shapes, wake characteristics, how much velocity is extracted from the wind through wind turbines, what happens in the wake. So these kind of questions we try to answer. Turbulence modeling is an important point in CFD simulations. Depending on our problem, we may select different approaches, from the direct solutions, direct numerical simulations, computing all the scales, towards the simplest model, algebraic models. So from the simplest to the highest levels models, you see different choices, right? So algebraic models, one equation models, two equation models, Reynolds stress models, 7 additional equations. They are called Reynolds average Navier-Stokes equations or simulations. They model all the scales, all the turbulence eddies. Direct numerical simulations, they compute all the scales. In between, large eddy simulations, now with the advancement of the HPC, usage of the HPC systems, we are able to do large eddy simulations. They take so much time, but they give more details about the flow field. They compute only large scales and model small universal scales. So they are called hybrid methods as well when you combine these large eddy simulations with the runs. So less runs methods, DES, SSM, some examples. I will just show one page of equations. So governing fluid dynamics equations, we are trying to solve our flow variables, density, velocities, energy, pressure, right? So conservative quantities in this integral form, finite volume approach we can use to solve these integral Navier-Stokes equations, which is 3D, unsteady, compressible, viscous with moving bodies as well. So we can have the body moving here component. And this viscous flux terms, so inviscid flux terms and viscous flux terms here containing the shear stresses that we need to model through the turbulence modeling. Okay, of course, for the gas equation, gas flows, gas dynamics, we can use the ideal gas equation of state to complete the system of equations. So to be able to solve such equations, let's here look at the Euler equations, inviscid Navier-Stokes equations in the differential form or in the integral form here. So we can use finite differences to estimate these differential terms in this equation. So in our grid, here you see a structured grid. So we can estimate the derivatives in the center point using the neighboring points, for example, using the forward, backward, or central differences, or in the finite volume approach. Sorry. We see a triangular cell here, for example. So in this cell, what is the average quantities? What are the fluxes going through this face of these cells, okay? How much mass is transferred, how much momentum is transferred through this cell. So this is the governing equation calculating those terms. This is how we find the flow variable Q at the cell-centered or not centered position. Okay, so after this small introduction, let me quickly go over these computational analysis tools. You will be able to get more information through these links, actually. As I said, we have this Indico training through EuroCC project. So the previous trainings, you can go and look at them. And also documentations, you can find more information related to different topics, actually, different HPC related topics there. And for CFD, this is our link here. So what is SU2? SU2 is a CFD software, an open source CFD software, multi-physics analysis and design optimization software. It is developed by Stanford University team. It was first called SU Square in 2013, and now, since 2016, it's called as SU2 as an open source CFD software, and you can get the code from the GitHub. There's SU2 Foundation for more information, trainings, conferences. This code is written in C++ and Python and can be run on Linux-based systems, and you can use them on Truba, ULAC-Beam HPC systems. Also, you can get the code here. Latest version is released in August 2022, version 7.4, and it's licensed under the GPL 2.1. On Truba, we have the 7.1.1 version, but you can easily install on your own account and use any version that you want. It's used in many areas of engineering and science. Both commercial and academic organizations use this code, actually. It solves Navier-Stokes equations using different turbulence models, Reynolds average, Navier-Stokes, DES, ADS you can perform using SU2. It also has adjoint solvers, so you can do design and optimization studies with this SU2 solver. Just a summary of the links related to this, and it's licensed under the GPL version 2. When you install that solver, this is what you see, file structure of the solver. Basically, SU2 CFD under this directory, you have all the source codes, you have test cases that you can try, and you can get some previous training events you can find on the Indico webpage as well. I will just briefly show you a sample job script that you can also find from the docs Truba. And using this job, you can submit your jobs to Truba system. You can check your queue. You can check the output of your job, or you can cancel the job. So some simple commands to get familiar with an HPC system. So we will see some applications of airfoil and rotor simulations with SU2 by using SU2. And in the afternoon, we will also see OpenFOAM applications. OpenFOAM is also another open source CFD software. It is developed as FOAM by in Imperial College in 1989. Then in 2004, it's called as OpenFOAM version 1.0. It's called Open Field Operation and Manipulation, actually, the meaning of the name. It can be run on Linux-based systems. It is being developed as ESI OpenCFD since 2012. So there are two web pages that you can get OpenFOAM. from OpenCFD webpage, latest version, and OpenFOAM Foundation, you can also get another version. So they are developed and released separately, so you can check which versions you need to use. It's also used commercially and in academic organizations. Can do runs, DS, LES, and also DNS for isotropic turbulence simulations. It can do 2D, 3D, multi-phase flows, chemical reactions, acoustics, electromagnetics flow simulations as well. So it is very widely used open source CFD software actually. So these are some important links that you can get for more information, user manuals, documentation, and training. It's written in C++ Npi as well, and SU2 is also written in C++ and Npi. And Python is also being used in these codes to compile and to do some hybrid calculations, let's say. There are different solvers in the FOAM. So it's called FOAM solvers. It's based on cell-centered finite volume method. Okay, here with OpenFOAM you can do pre-processing a little bit, so you can use some meshing tools to create your grid, solving using the different solvers, and post-processing using ParaView or other similar visualization software. So just a sample CFD steps: geometry creation, model, and geometry is created here. Grid generation, you can use block mesh, snappy hack mesh, or if you use other mesh generators, you can also convert your mesh to OpenFOAM format, or you can map different solutions to your mesh as well using utilities here, as you can see, some sample utility. For visualization, your solutions can be written in ParaView format, or you can convert them to any other formats as well to view the flow field solutions. How it looks like when you open the software, these are the main directories, applications. You have the solvers, different solvers, utilities, and tests, also tutorials, as you can see here. So I will not go into detail, but you know, it's not very complicated. They all look similar. That's why I wanted to show you both SU2 and OpenFOAM. So they all look similar. Once you get used to using one of them, it will be easy to learn the other codes as well. Okay, so some directories, some utilities, and other applications. And we have done some trainings on OpenFOAM. So previous 2 trainings actually you may see on Indico webpage. Okay, today last application will be the OpenFast. So it's not a CFD code, it's a little bit different, but it has been highly used in wind energy analysis, and it's actually based on the blade elements momentum theories, okay, and with more corrections, let's say, like it may include free wake corrections, or you may do some wind farm analysis. So it's called an open source wind turbine simulation tool. Started in 2005. Since 2005, and the last version of the FAST, the first previous name was the FAST, so it's not version 8.16, and then it changed into OpenFast version 1.00 in 2016. Okay, and since then it has been developed as OpenFast. It's a multi-physics, multi-fidelity tool for simulating the coupled dynamic response of wind turbines, and can be run on Linux-based systems. You can get the codes from GitHub, latest version, as you can see, with the Apache license 2.0. There is also OpenFOAM. Sorry, this is wrong. Okay. There is also OpenFast community that you can get many documentation from the NREL. So it's developed by NREL. GitHub page and documentation page, read the docs page, you can get more information. Today we will see some applications. So I will just show you a list of the modules that we have in OpenFast. We can do aerodynamic calculations based on the blade element momentum theories. We can do aeroacoustic noise calculations, free vortex wake. Inflow wind module can generate complex turbulent inflows, or TurbSim can also create turbulent wind conditions. I'm almost done. And wind farm module is the new module, actually. We can simulate or model wind farms using fast.farm. There are also structural models, which has a finite element-based blade structural dynamics module. It's a time domain structural analysis you can do for the substructures as well. There are other modules or models for the support structures using super elements, and Elastodyne is using the structural dynamics module, again, actually using all the governing equations of motion to model your dynamic wind turbine system. There is also hydrodynamics model. We will talk about this today. And you can also model the servodynamics and other structural control components, dampers, through this code, let's say. Okay, so this is the end of my introduction, actually. We will, what time is it? Are we on time? Maybe a little bit late, okay. So we can continue with Ezgi. The next presentation will be given by Ezgi or by Akçeniz. She's a PhD candidate. She's also an instructor at the RUZGEM, working at RUZGEM. So she will talk about wind turbine airfoil CFD analysis. And after that, we will take a break, a short break, and then we will then talk about the rotor CFD analysis by Ali Ata Adam, research assistant from the Aerospace Engineering Department and working at RUZGEM as well. And we will have lunch break and continue. Okay, thank you. If you have any questions, maybe after Ezgi's presentation, we will get all the questions. Okay, we'll try to answer them. Thank you. Ezgi.
Merhaba hocam.
Merhaba.
Videoyu başlatamıyorum ama.
Dur ben şunu, I need to I need to stop my sharing, right? Pause share. Okay. Okay, I did it. Now you should be able to share your presentation.
Bir dakika hocam.
Okay, there are two questions. Maybe I can try to answer while you are getting ready. Maybe I missed during presentation for blade design, which software or method can we use? As I see before CFD analysis, the blade design needs to be finished. So that's why we have OpenFast. Basically, OpenFast is one of the software that's being used widely for design of the rotor blades or rotor whole turbine system, actually. So in the afternoon, we will see some applications. How rotor azimuth angle affects vortex formation? Can it be used for turbulence control at wind farms? Well, you mean as the rotor blades rotate, they change the azimuthal position? Okay, if you control the pitch of the blade, maybe that's what you mean. Then you can control the vortex formation as well, of course. So it can be used in for power generation. It's being used Therefore, for wind farm flow power generation, it's being used as well. There are new recent studies for wind farm flow control strategies for wind farms using these kind of approaches. Yes. Thank you.
Can I start now?
Yes, please. Okay.
Hi everyone, my name is Ezgorbay Akcengiz and I will present the wind turbine airflow safety analysis part. Here is my content.
Can you, Ezgi, do you have your camera? Maybe you can.
I couldn't start it.
Okay, maybe they can help you. Maybe they can help you. Sezan, can you help?
Oturum sahibi durdurduğu için videonuzu başlatamazsınız diyor.
Nile hocam, you have the authority to
Can
let
I? Okay.
That is, yes.
Okay, how do I do it? Okay, I will make you co-host maybe.
Yes, maybe you can
Okay.
make co-host.
Yes, then you can open your camera. Thank you. Great, thank you. Hi from Ruzgem.
Okay, hi everyone again. My name is Ezgorbay Akcengiz and I will present wind turbine airflow safety analysis part. Here is my content. After a brief introduction about safety simulations for airflows and computational grids, I will show the steps of how you prepare your safety analysis in SU2. And then I will present a simple case by using a thick wind turbine airfoil. Aerodynamic design of a wind turbine rotor is mostly based on fast plate element momentum theory analysis. It requires accurate lift and drag polars for a wide range of Reynolds numbers. For a typical modern nonlinearly twisted and tapered blade, there is a usually distribution of a family of airfoils along the radius. Airfoil aerodynamic characteristics are generally obtained through a combination, numerical simulations, and wind tunnel tests during both airfoil design and blade design processes. Because of limited availability of wind tunnel data in limited Reynolds number ranges, obtaining accurate numerical results is of vital importance. To start the safety analysis, at first we have to prepare the computational mesh. Here, you can determine your problem is 2D or 3D, and you can choose your mesh topology and grid cell type. After that, you can export your mesh, computational mesh for your CFD solver. Here, you can choose your solver. For example, you can solve the Rans equations or LES equations. Then you can change your turbulence models and you can choose transition if you use transition model or not. You have to determine your free stream conditions and boundary conditions definitions, and then you can define your numerical method and time integration, and you can change your linear solver if it's available, and you can determine your convergence criteria. After that, after you run your simulations, the post-processing parts comes. The results can be compared in quantitatively with experimental data by drawing graphs or using tables. And also you can flow field can be investigated by contour plots and streamlines, or you can use vectors, velocity vectors. In CFD analysis, there are three important aspects: numerical solution approaches, turbulence models, and grid characteristics. In numerical solution approaches, there are 2D and 3D. You can solve two-dimensional, three-dimensional problem by using runs or alias equations in steady state or unsteady. And also in turbulence model, there are multiple choices. In runs, splat runs, KMOG, SSD, and realizable KFSOM are commonly used ones. And also, besides of runs and alias, you can use hybrid models. In grid characteristics, depending on your problem, there are structured, unstructured, hybrid, or block structured for multiple block choices. In two-dimensional simulations, you can use O-type, C-type, or CH-type structured grids. And in three-dimensional simulations, two-dimensional grids are extended in span-wise direction. One of the critical steps of CFD analysis is generating the proper computational grid for the problem. Depending on the geometry of the model and solution approach, type of grids can be changed. As mentioned before, they can be structured or unstructured and so on. Also, the solution should be independent of computational grid as possible. Therefore, grid independence study is performed. Grid size is increased and decreased by a constant factor in every direction systematically. For a structured computational mesh, generally grid size are changed with a factor of square root of 2, so the area of a cell is doubled or halved in a two-dimensional simulation. The change in the cell edge size is performed for every direction by keeping the growth ratio as constant. You can see a simple grid independence study. These are grid 9, 8, 7, and 6, 5, 4 from coarse to fine. And here you can see the grid 6, 5, 4, and 3, 2, 1 from coarse to fine. And you can see the zoomed view of a coarse grid. And these images belong to a fine grid. Here you can see an example of grid independence study. There are 9 grids generated, and you can see that as linear part, the results are very close to each other. But as angle of attack increases, the difference increases. And also you can see that in difference in direct coefficient with respect one of the grids, which is taken as grid 3. You can see that as angle of attack increases, difference in the direct coefficient is also increases. As mentioned before, you can see that as a small angle of attacks, the results are very close to each other. And I want to talk about one of the open source CFD solver, SU2. SU2 is a computational analysis and design package that has been developed to solve multi-physics analysis and optimization tasks using unstructured mesh topologies. Compressible and incompressible Euler and Navier stocks can be solved by using Browns, LDS, or DDS solution methods. And also, the turbulence models for runs equations are available in SU2 are splat almaras with transition model, and KMOG SSD. In order to run a simulation, a simple CFD simulation by using SU2 in Turbo, you need 4 input files: mesh file, configuration file, JavaScript, and make clean file. And depending on your problem, as output files, generally you will have volume flow, surface flow, history, convergence history, and restart files. In mesh file, you have to define your dimension of the problem and also information about the elements and nodes and boundary conditions. In the information of the elements, you should identify your grid size. For example, 5 is given for triangle, 9 is given for quadrilateral, and so on. Here you can see a sample mesh file. You can see that our problem dimension is 2 and number of elements is given. And you can see that some of the elements are quadrilateral because it's given as 9. And also number of and node coordinates are given, number of points, and you can see the coordinates. Also, boundary conditions should be defined in boundary elements part. You can see that we have 4 boundary conditions for this problem. One of them is wind tunnel walls, and number of elements are given. And also here 3 is given for that these elements are line because it's 2-dimensional problem. And in the configuration file, you can, as mentioned before, you can choose your solver as runs, Euler, Navier-Stokes, or so on. You can change your turbulence model, and you can state your problem is restart or not. Also, in this part, you should define your free stream conditions as Mach number, angle of attack, temperature, Reynolds number. And here, you can define your boundary conditions. Here we have wall boundaries for airfield and wind tunnel walls, and far field boundaries for inlet and outlet. And also you can choose your surface where the functionals, for example, drag coefficient or lift coefficient, will be evaluated. Here we choose is as airfoil. Also, you can change your CFL number and iteration number, and you can change linear solver, a BCG step, FGMRS, and also you can choose your preconditioner. And also you can change the convergence criteria. Here you can, you should state your input and output information, such as the Perkins-Solve solution file or the type of the output file format, and also screen output, history output, and output files as well. Now I want to show you some results of sample test case. In this sample test case, CFD simulation for a thick wind turbine airfoil are performed at high Reynolds number. Sectional Reynolds numbers for large wind turbine blades can be as high as 15 million. And experimental data used for this study are available in the literature. You can see that in the literature, there are 7 different test cases with different Reynolds number and Mach number. 2 different solver is used, CFD++ and SU2. Computational mesh is structured O-grid. 2-dimensional compressible steady-state run simulations are performed. And boundary conditions are given as, for airfoil surface, wall boundary condition is applied, and for far field characteristic-based inflow-outflow boundary condition is applied. In CFD++ simulations, Kawamaki SSD turbulence model is used, while in SU2, Spallard analysis with a transition model is used. And simulations are performed for 3 different Reynolds number in CFD++, and in SU2, the simulations are for just the Reynolds number 3 million. Here you can see this. You can see some results in terms of lift coefficient and drag coefficient with respect to angle of attacks. The results are given as a comparison with the experimental data. Here, in linear parts, the CFD results are very close to the experimental data, but as angle of attack increases, stall angle of attack is shifted in CFD. Is shifted to high angle of attacks, and also this maximum lift coefficient is over predicted. And also you can see the under prediction in drag coefficient in higher angle of attacks. These results are obtained from the CFD++, and you can see some counterplots with streamlines for 3 different Reynolds number and two different high angle of attacks. You can see the recirculation regions increases as angle of attack increases. And you can see the magnitude counterplots for 6 different angle of attacks from 0 to 20. The vortex magnitude is increased as angle of attack increase. Here you can see the results for the results obtained from the SU2. As in the CFD++ case, maximum lift coefficient is over-predicted, and also stall angle of attack is shifted to high angle of attacks, higher degrees. And also you can you can see that the under prediction drag coefficient for high angle of attacks as in the CFD++. Similar results are obtained, we can say that. And also you can see the pressure coefficient distribution with the streamlines for different angle of attacks from 0 to 20. For this problem, the angle of attack is given as an input in the far field. Therefore, the airfoil is horizontal and streamlines are just like that. You can see the recirculation region. Also, the same airfoil is analyzed in a wind tunnel in METU RUZGEM. 2D compressible steady state run simulations are performed using SU2. Spolar unmasked with boundary condition, with PC transition model is used as turbulence model, and in boundary conditions, as in the airfoil surface and wind tunnel walls, wall boundary condition is used, and for inlet and outlet characteristics based inlet and outlet far field boundary condition is used. Simulations are for 3 million, and you can, this is still an ongoing work, so you can see some results. Here, Reynolds number is 3 million and Mach number is given as 0.074. You can see that as angle of attack increases, the similar pattern is obtained as in the previous case. You can see the angle of attack increases, the recirculation area is bigger. Also, the parallel performance analysis is done by my colleague Ezgi Aslan. Computations are performed for different grid size using different number of processors. Serial runs are performed in turbo cluster Lebrek, and parallel runs are performed in turbo cluster Barbun and Hamsi. For serial runs, you can see that as number of cells increases, the computational time, the wall clock time also increases. You can see the grid numbers and the grid sizes. In parallel performance analysis, there are 2 parts, speed up and efficiency. Speed up shows the performance of a parallel algorithm. It is the ratio of the serial time and parallel time. For parallel runs, the speed up increases as the number of processors increases. After a certain number of processors for a given grid size, the communication time between the processors becomes significant. In efficiency part, efficiency shows the load balance and communication. It is ratio of speed up and number of processors. For good efficiency, suitable combination of grid size and number of processors should be selected. Suitable workload, which is number of grid cells per processors for a given number of processors, need to be selected to balance the computation and communication for high efficiency. You can see the graphs for speed up and efficiency. As number of processor increases, the speed up increases, especially for the finest grid, which is grid 1. And also efficiency, you can see that as processor number increases, efficiency also increases. And you can see that again, speed up and efficiency graphs with respect to number of processor and number of grid cells respectively. For grid 1, the number of processors 64 is the maximum, gives the maximum speed up. You can see that. And also as number of grid cell size increases for 64 processors, efficiency, you can see that the blue line shows that it increases. In conclusion, in this presentation, wind turbine airflow safety analysis are explained briefly. Grid generation and solution methods are discussed, and also grid independent study procedure is shown. The steps of how to run a simple simulation using SU2 are presented. Also, the results for a simple sample test case for a wind turbine airflow are presented. Parallel computational performances of SU2 runs are also discussed. Thanks for your kind attention. If you have any question, I can answer that. Hocam sesiniz kapalı.
Okay, thank you, Ezgi. We have some time. We can look at the questions. Maybe there's a question. Which type of elements do you apply on far field in those kind of 2D mesh applications? What's your...
For the all grids, we have structured cells. We have structured cells. Here, quadrilateral cells are used. And for far field boundary, you can see that there are line elements because it's two-dimensional.
Mm-hmm. So, is that okay? If it's not clear, you can write comments. Again, we can try to answer. Thank you. Thank you for presentation. Did you try to make any analysis for counter or parallel rotating twin rotor wind turbine? Is the process more different from single rotor designs? Would you like to answer?
I didn't rotor.
You haven't done it, two rotors, but I mean, it is possible. We have done for the helicopter coaxial rotors. We have done a simulations with SU2 in one of the conferences last year. So in this case, you have two domains. Actually, in the next presentation, maybe we will have rotor simulations, so we can answer there as well. So you will see how we try to simulate rotors in 3D. So you can have twin rotors as well, or twin wind turbines as well. Yeah. Can we capture the stall in CFD with a transient solver?
Yes, it is possible. In the literature, you can see that as using a transient solver, for example, EUROCC. They obtained closer results to experimental data.
Mm-hmm. Actually, there is a new handbook of wind energy. You can find many information, many literature reviews there, recent studies. Maybe you can check that as well. Yeah, of course, with unsteady solvers and also transition models, different transition models can be applied to estimate, to improve the stall estimations, but it's really difficult. I mean, still, I guess you need to go to the LES type of simulations, right, for more accuracy.
Yes.
For stall conditions.
Yes.
Why do you think CFD++ fails for airfoil simulation at higher angle of attack? Yes, similar question. Yeah, this is what you expect from classical runs simulations. Reynolds
Steady state runs.
This is what you get actually from any software, any CFD software. It's really hard to obtain stall conditions. You need to do unsteady simulations or LES type of simulations for more accurate results, but it's more expensive, of course, for design studies. So, yeah. Okay, so thank you. Any other questions? Okay, I think we have a break as well, so we have lots of time left actually. So we can try to answer more questions or any comments. Yeah. The CFL limit on the study looks rather high. Have you also checked different CFL numbers and their effect on results? Yeah, very good question. Ezgi?
It is steady state. Özlem Hoca wants to answer that question.
No. She's just checking. You can answer.
Okay. These simulations are steady state simulations. Therefore, CFL number can be high. So, and also this number is given as an example. Actually, it can change according to your problem and according to your grids.
For different, so for example, Ezgi tried different grids, right? From coarse grid to fine grids. In each case, you need to adjust your parameters. Actually, also, yeah, for different grids, it will affect the solution as well. So it takes really time to get accurate results. You need to try different parameters, different limits. But for steady state solutions, for run solutions, if you are using implicit methods there, Ezgi, for example, if the CFL number can be high in those numerical algorithms, numerical methods. But if you are using unsteady explicit simulations, then your CFL might be limited. In that case, you need to start with lower CFL. Maybe later on you can try to increase it a little bit. Yeah. Okay, thank you. Nice, another nice question. Have you used pressure or density-based solver for CFD++ simulation? Does it make a difference?
I didn't compare them. In CFD++, it was pressure-based, I think. I remember. But I didn't compare it with the density-based solver.
But didn't you use the far field boundary conditions? I remember, I think you used density-based solver, right? We usually try to use density-based solver if possible, instead of having the pressure-based solvers. It's more robust. It takes time or difficulty sometimes, but you will have better results. Yeah. Ezgi, I guess you used density-based. I remember like that, but we can check. Yeah. You can check the papers. VESC paper, VESC presentations, maybe for more detail. Okay. Okay, let's take a break. We have coffee break, so we can meet again at 11:30 for the next presentation. Thank you. Merhabalar tekrar. Hi. Hello. Ata, are you here?
Yeah, I'm here, Hocam.
Hi. Hi. If any questions, is there any questions, we can try to answer while waiting a few more minutes. Maybe I can start introducing. So we will continue with the next presentation. It will be about wind turbine rotor CFD analysis. And Ali Ataadam will present. He's a Master of Science student and also research assistant at the Department of Aerospace Engineering. And so he will talk about applications, how you can simulate rotors, wind turbine rotors using SU2. Ata, if you want, you can share your presentation now.
Okay, Hocam. So I think it's on time. So can we start?
Yeah, we can start. Yeah. Okay.
Okay. Hello, everyone. So as you know, I'm Ata. So in this presentation, I'll talk about the wind rotor CFD analysis by using SU2. So I'm planning a 40-45 minutes of presentation, and then you can ask your questions. I think there will be plenty of time for that. So I divide the presentation into three. First, I'll talk about wind turbine rotor aerodynamics and CFD implementations. Of course, Dr. Cesar Luzo truly explained wind turbine aerodynamics, but I want to emphasize more about the parts related to rotor CFD. Then I'll go on with the SU2 capabilities and tutorial, and at the end, I want to show some applications. So in this section, I'll start with flow over the blade, then I'll continue with interactions with turbine components and non-turbine elements. Then I start to talk about the wakes, and I'll finish it with additional considerations. So for a commercial wind turbine, what I mean by commercial wind turbine, like the new turbines, installed in 2019, 2021, in recent years, we see a tip Mach number around 0.2. So as you all know, I think the incompressibility assumption is valid up to Mach number 0.3. So we see that the incompressibility still persists, so we can use incompressible flow equations. But when we see the trends of rotor diameters over the years, we see that we can see this tip Mach number reaching 0.3. So the compressibility is knocking on the door. So if you want to simulate a very large wind turbine like 50 megawatts, 10, 20 megawatts or more, maybe it's better to use compressible flow equations. And about the angle of attack, so we have the radial distribution of angle of attack of the DTU 10 megawatt wind turbine. So let me open my laser pointer. Yeah, so this is DTU 10 megawatt wind turbine. So we have the angle of attack plot coming from blade element momentum and CFD results in the literature. So when we look into the first 30% of the blade, inner 30% part, we see some very high angle of attack, greater than 10 10 degrees. So we can say that we exceed stall angle over here near the root. But we still in the linear regime at the mid and tip sections. But this part is quite important in CFD application. I'll talk it in a few slides. The same wind turbine with the same wind velocity. So now we have the Reynolds number distribution or the blade. So we can see that in most of the part of the blade, the Reynolds number is in the order of 10 million. So which is quite high. So this is an offshore wind turbine. Of course, it's quite big. But what about small wind turbines? So of course, we will not see Reynolds numbers as high as 10 million, but probably it will be in the order of 1 million. So it's still high. So we need high turbulence resolution in our CFD applications, in our meshes. And separation. So as I talked earlier, so we have high angle of attack in the root section. So this is the same wind turbine DQ 10 megawatts. And in this CFD application, we can see the streamlines over the blade. And in this part, we see some significant flow separation over here. So due to high angle of attack and very thick airfoil. So for example, in the station, we have a 36% thick airfoil. It's quite high compared to, aircraft wing airfoils. So we see some separation near the root in most of the wind turbine blades. And also we have laminar turbulent transition. So for small wind turbines, as I told you earlier, we have lower Reynolds numbers. So we may see some laminar flow on the blades. So it could be better to consider a laminar turbulent transition models in our CFD simulations to see the effect of laminar flow to increase the accuracy. But for large commercial wind turbines, you have both high Reynolds number and leading edge roughness erosion in reality, which forces an early transition. So it could be, usually in literature, we see some fluid turbulent flow applications for large commercial wind turbines. You may try transition models, it's no problem, but in most cases for large turbines, we see similar results with and without transition models. Interactions with turbine components. So we talked about blades, but apart from blades, of course, we have other components in turbine. We have a spinner at the front, we have the nacelle, we have the tower, and obviously they will interact with the flow and also the flow coming from both rotor and the incoming velocity. So we have this CFD applications only with blade and with the remaining parts of the turbine. So when we look into the wakes of the single blade, just the blades without components, we see some symmetrical wake profile. So it's symmetrical and it does not break. The mixing is limited. And also we have this jet increased velocity in the center because of the lack of any component over here. But if we include the remaining parts, then it's a totally different picture. So we have this unsymmetrical shape because of the interaction with most of the turbine. We have some reverse flow behind the nacelle and also the tower. And also we see that the jet in the center disappears. Instead, we have even a more velocity deficit because of the nacelle. So if you want to simulate the wake behind the wind turbine, then it will be better to include these components because we have some drastic changes. But in another view, when we look at the velocity over the blade, we see similar velocity profiles compared to these two cases. So this will result in similar power and thrust values. So if you want to, let's say you design a blade or you optimize a already designed blade and you want to see its power curve, then it could be better to just mesh around the blade and then simulate it. So it will be computationally cheaper. It will require less pre-processing time. But if you want to simulate more turbines, like if you want to put another turbine over here, then you may need these components. So it depends on your application. Also, we have non-turbine elements like the ground. So if you're trying to simulate multiple wind turbines in a real terrain, mountains area, or you want to do a wind farm placement application, then you should include such elements because the complex terrain will change the velocity distribution over the area. Similarly, we have offshore wind turbines. So this, of course, the sea is flat. It's okay, but we have waves, of course. I'm not an expert in offshore wind turbines, so after the lunch break, there will be more detailed presentation about it. But if you want to do an offshore wind turbine analysis and want to include the effect of the sea or the foundation of your turbine, it would be better to couple it with a hydrodynamic solver, because the change in angles would obviously affect the aerodynamic properties. Also, we have the atmospheric boundary layers. For the ones who do not know, let me explain it briefly. So it's similar to the boundary layer on a wall. So we have the ground, the surface of the Earth, and there will be zero velocity. And when we get higher, like 100 meters, 200 meters, maybe 1,000 meters, then we would see a uniform flow maybe. But in between, we should have a velocity profile, which is called atmospheric boundary layer. So it is actually a non-uniform net velocity profile. So on the right-hand side, we have several simulations of RL phase 6 wind turbines. So on the upper left side, we have no shear flow, no atmospheric boundary layer, just a uniform flow. We see a uniform wake going straightly and breaking in a later downstream distances. But when we add the atmospheric boundary, like the results on the upper right side or lower side, we have an asymmetrical flow going upwards and an earlier wake breakdown. So it affects the wake and turbine performance along with the incoming flow velocity and turbulence. But if you are simulating a very large wind turbine, then it may not affect the turbine performance. So because the rotor may be outside of the atmospheric boundary layer. So if you're, if you want to simulate a small wind turbine, then the effect may be tremendous, but otherwise it could be negligible. It depends on the application. And also the wakes, of course, I talked a lot about wakes. They are very important, especially in wind farms. So behind downstream of the turbine, we see a reduced velocity and increased turbulence, which affects the wind turbine performance of the wind turbine performance. And also we see some tip vortices emerging from the turbine rotor. So they are quite important as well. So let's say you want to generate a mesh of a wind turbine rotor, then it will be better to still have a fine mesh, not just at the tip, but also at a little bit above the rotor blade to resolve these tip vortices. Also, the wakes is highly affected by the wind turbine control. For example, here we have two different cases. So in the blue line, we have no wind turbine control. This is by the way, the power generation coefficient with variation with time. So VT1 is the upstream turbine and VT2 is the downstream turbine. But if we include the wind turbine control of yaw misalignment to the upstream turbine, we see some degradation of the power for the upstream turbine, but an increased power production for the downstream turbine. So that's why it's important to model wakes if you want to do a multiple wind turbine simulation. From the same work, this is actually the image of the wake. So we have some unsymmetrical wakes, as you can see, some partial misalignment. So these are also quite important, which affects wind turbine performance. Apart from that, I talked about surface roughness earlier at the transition part. So in reality, we may have leading edge contamination and erosion, which causes some degradation of the wind turbine performance and earlier transition to turbulence. So you can see some effect of power. So the black lines are clean configuration, but if we add some surface roughness, we have lower power production. So in CFD applications, you may directly model the surface roughness in your mesh, but which is quite complex and could be hard. So you may apply roughness models included in flow solvers. Also, we have aeroelasticity in consideration. In other words, fluid structure interaction. So if you have a very large wind turbine rotor, then you may have tremendous deflections, which would affect aerodynamic attributes. So this is quite actually complex, but if you want to include, you have to also include some structural solver coupling in such a case. And so nowadays we have novel wind farm control methods apart from just yaw misalignment. So such methods require high fidelity CFD simulations to see the effect of control. Gusts are an important matter as well. It is a brief increase in the speed of the wind. So they are included in many rules and regulations of wind turbines. So on the right-hand side, this is a PIV measurement of a wind turbine experiment in a wind tunnel. So you can see that the change of the wake with and without gust. So it may reduce the effectiveness of the wind turbines and also the wake. So it may be important to model them as well. And also we have aeroacoustics. Again, in the rules and regulations, if you are designing an onshore wind turbine, you have to limit your sound emissions, and to test that, you have to do CFD simulations with aeroacoustic solvers. This is also another consideration. Okay, so this was the the summarize of wind turbine rotor aerodynamics. So we can go on with SU2 capabilities and tutorial. By the way, this will not be a total complete tutorial. I just want to emphasize the things related to rotor CFD. But still, I have to give some fundamentals. Then I will go on with dynamic mesh, some considerations related to flow over the blade and interaction with rotor components. Also, I want to mention the models of actuator disks, surface roughness, and gusts in SU2. So SU2 is actually a very simple program. It requires just two inputs. The first and the main one is a configuration text file. So you can see some part of a SU2 configuration file. So we indicate our settings as such. And we use this configuration file through the command we do in command window. So SU2 CFD is the CFD solver of SU2, the application. So when you write this command SU2 CFD, you have to put the name of your configuration file, and when you enter the SU2 simulation begins. It's very simple. If you want to do a parallel simulation, you have to include Npi run with the number of processors with the -n setting. And so there are Python scripts in the root folder of the SU2 to run it with multiple commands. So you may also want to look at that, but I won't get into much detail about that. And the second input is the mesh file, but we call it through the configuration file. So this is the part where we define the mesh file. So we have the mesh file name setting, and we put the name of the mesh file. And also the format. It could be the SU2 native mesh format, and you can see some part of that file. And also we can use CGNS. So as I know, most popular mesh generators have the SU2 file format, so you can just directly export SU2 meshes. But of course, in some, you cannot find such a setting, so you can use the universal CGNS format to run your simulation. SU2 uses an outer time loop to march through the physical time in an unsteady simulation, and an inner loop, which is usually a pseudo time iteration or a quasi-Newton scheme. And you can define the time dependency with time domain setting. If you put no, it will be a steady simulation. It will do only an inner time loop without an outer time loop. Or you can write yes for an unsteady simulation. The number of iterations are controlled differently. For a steady simulations, you have to write iter and give the number of maximum iterations. For unsteady simulation, we have the settings for time steps in seconds, maximum time in seconds, number of maximum inner iteration, and maximum outer time iterations. And the simulation time will depend on these parameters. So it will take the minimum of these two terms. The first term is the multiplication of the maximum time iteration with the time step, and the second one is the maximum time. So in this case, the first term will be 200 seconds, and the second term is 50 seconds. So SU2 will take the minimum of that. So in such a case, our simulation will run for 50 seconds, and with a time step of 1 second, it will be 50 iterations in the outer time loop. And also we have some time marching methods for solving differential equations. If you look into the tutorials, you'll see most of dual time stepping of second order rule is used, but I won't get again much detail about the mathematics. If you are interested in that, you can look into the documentations of SU2 website. And also boundary conditions are crucial as well as a fundamental. So for a no-slip condition of a wall, we usually use constant heat flux wall, a boundary condition. So we put the name of the boundary condition indicated in the mesh file, and also the heat flux. So in this first boundary condition, the feed flux is given in watts per meter square. And also if you have more than one marker for your no-slip condition, you can just put it like that, just put a comma and go on with it. Usually we use adiabatic flow if you do not want to include any heat transfer. Also we have other no-slip conditions, but this one is the most used one. If you want to put free stream values as your boundary conditions, you can use far field boundary condition as marker far. It just needs the name of the marker without any input. For the outlet, again, we have marker outlet. It requires similarly 2 inputs. The first one again is the marker, and the second one depends on the outlet type. It could be compressible, incompressible pressure, incompressible mass flow. It depends on your selection. Again, similar to outlet, we have several inlet types, total conditions or mass flow. Again, it depends on the compressibility of the flow. We define the conditions with marker inlets. This time we have more than 2 inputs. Again, we have marker. Then for the total condition case, we have to specify total temperature in Kelvin and total pressure in Pascal. Also, we must indicate the flow direction as a unit vector. For the mass flow, the total temperature and total pressure change to density and velocity magnitude. Again, as I said, we also have incompressible case, but I did not put it in the slide. I talked earlier about the atmospheric boundary layer. It is a non-uniform inlet profile, but these cases gives uniform inlet profile. So if you want to give a non-uniform boundary conditions, you can use this specified inlet profile option. So if you enable it, the SU2 will search for the inlet file whose name is specified in the configuration file. If SU2 cannot find such a file, it will generate a template file. For example, you indicated inlet as a marker name. So you put inlet type, total conditions, marker inlet with all the numbers, and also you enable this profile and you run the simulations. But if there's not an inlet .dat, SU2 will stop the simulation without running it, without going it further, and it will generate a template file. If you open that file, you see that all the points are taken from this inlet marker you specified in this marker inlet. So you can use them both at the same configuration file, even if you enable inlet profile. Then you get the template file, change the velocities, and put it in the same directory, inlet dot, and then SU2 will take this file as the inlet profile, even if you put this 2 options. So it's quite useful if you want to do a simulation with a non-uniform inlet profile. Also, we have periodic boundary conditions. So probably the CFD people will know what this means, but for the ones who do not know, I will explain it with some annotations. So let's say that we have this wind turbine, right? A tribulated wind turbine, and we have the far field boundary condition, and we do the mesh, we simulate it, it's all fine. But at the end, you will see that if your simulation is, you simulate that for enough time, the flow around each blade will be similar. So in some cases, it will be okay to just simulate one blade with 120 degrees of simulations, like here. Let me erase them. Sorry, again, sorry. So you have the blades, you have the boundaries. In such a case, you have to define periodic boundary conditions for the case where there is periodicity over here. So in our case, we put periodic marker and donor marker. We have a periodic marker and donor marker. We indicate rotation centers and the rotation angles. In our case, it will be 120 degrees. So it will contains less cells, which will come with a less computational cost. So this is good in terms of computation. But there's a problem. So if you do not have identical surfaces, so if you just revolve, by the way, what I said 120, right? This will be 240. Sorry about that. Anyway, so if you do not have any identical cells on the surface, then SU2 will try to interpolate the cells to make a connection, but it will end up with bad quality cells, which may result in divergence. So it is important to get an identical cells for such a case. So these are the boundary conditions, and also I want to talk about some outputs. So SU2 gives mainly three outputs: history output, surface flow, and output flow to see the results. And it gives flexibility for the user to put which outputs and which in which output file. So for your case, you can list all the possible output fields with this command. So with this -d option, you can perform a dry run, and at the end, SU2 will list all the possible output fields. For example, in a rotor application, you can put rotating frame, which includes figure of merit, thrust, torque, and also vortex identification, which gives vortices. So before starting your simulation, you may just want to run this command and see if there is any output you want to see in your output files. Okay, so let's continue with dynamic mesh. Of course, we are doing a rotor application, so our mesh must be dynamic, of course, and we can define this dynamic mesh with grid movement option. So we have rigid motion, rotating frame, steady translation. So rigid motion corresponds to a physically rotating mesh. You just, at each time step, SU2 revolves or translates, depends on the application, moves the mesh. In a rotating frame, it does not physically rotate the mesh, but it includes rotational force source terms in the flow equations. So you can make steady simulations with rotating frame, but there will be differences in the results, and I will show it in the applications part. And steady translation is similar to the other case, but it does not include rotation. So this is not related to the rotor CFD applications. And also in a dynamic mesh, you have to define the Mach motion for the initialization, motion origin, and rotation rate in radian per second. So for example, in this case, we indicate that the mesh rotates with 5 radians per second in z-axis around this origin. I talked about the transition models earlier. So SU2 contains 2 transition models, spread anomalous BC and lengthy-mentor transitional SSD. So about a week earlier, SU2 published their new version 7.4, and starting from that, the indication of a BC transition model changes to SA option. So if you are using SU2 earlier than version 7.3, you should indicate BC model as such, but if you just download it in this week and compile it, then you have to use this option. And also, I know that earlier the developers closed the option of LM transition model, but I think starting from version 7.4, they enable it again, but I'm not sure about that. So I didn't personally try this, so you can try that. And if you want to use this model, if it's closed and you still want to use that model, you can download the earlier versions of SU2. But I think earlier than 7.3 for the 7 and 7. After that 7.0, this option is closed, but it could be opened for this version. And also you have to include the turbulence intensity, because this term is used in the transition models and it is an absolute value, not in percentage. So 0.05 means 5%. And also we have wall functions. So you meshed your wind turbine, you put some boundaries, or you even didn't put any boundary layer, but there's separation, there could be transition. So it is important to resolve the boundary layer finally. So the rule of thumb is that Y plus term should be lower than around 1. So you can make that with wall functions without resolving the mesh in a fine manner. So we indicate wall functions as marker wall functions in SU2. And also we have some constants and some criteria. So you can use that. And if you want to test that, you can do 2 different meshes with a fine and coarse mesh. And in the coarse mesh, you can implement wall function and see the differences. Okay, so I talked about dynamic mesh, but in wind turbines, there are components that are not rotating. So we have the blade rotating and, for example, tower nacelle not rotating. So how can we, rotate some part and not and keep it still some part? So in such a case, we have to specify different configuration files for different components. So in the main configuration file, we indicate multi-zone, we enable multi-zone part, and we indicate the name of the configuration files of different parts, so non-rotating and rotating parts. And also we have to include the interfaces. This is like the boundary condition. And also you can discretize, mesh each zone independently. And so you can specify the kind of interpolation you want SU2 to manage between these interfaces. And then in different configuration files, you can give different grid movements and different mesh files. So with these two, actually we have main configuration file, two different configuration files for rotating and non-rotor components. So at the end, we will end up with 3 configuration files, and with calling SU2 CFD with the main configuration file, you can simulate turbines with rotating blades and other components. In SU2, we also have an actuator disk model, but it is not very suitable for wind turbines. It's developed for mostly propellers, but still usable for wind turbines if you want to. So we define the actuator disk similar to boundary condition with act disk, marker act disk comment. We also define the type and the file name. So we have to give the properties of the actuator disk in a separate text file. So we have the radius, axis center, but also we have the advance ratio, which is most related to, as you know, propellers. Also, we have to give the derivative of CT and CP in the radial direction. So in wind turbines, we usually give CP and CT with respect to wind speed. So this is different than conventional wind turbine applications, but still you can get an actuator disk result with SU2. So, and also, so the beauty of open source is you can, change this model. So you can just try to work on that, develop a wind turbine model for actuator disk implement SU2, and you can email it to the developer, said that, okay, I developed this model, it works fine, you can see the results, and maybe in the next public version, your model could be, in the SU2 flow solver. I told earlier about the surface roughness models. SU2 contains such a model as well. You can define the wall roughness with the equivalent centigrade roughness height in meters. And also we have a gust model in SU2. You can define top hat sine, 1 minus cosine, and etc. shapes, but it only works in 2D. So this is not very applicable for rotor applications, but the developers are working on for a 3-dimensional model. Okay, so this was the end of the SU2 tutorial and capabilities. So now I want to show you some applications with a wind turbine rotor. So our test case is NREL phase 6 wind turbine. It's a tubulated wind turbine with a rotor radius of around 5 meters. Its rotational speed is 72 RPM. It consists S809 airfoil starting from the first quarter of the wind turbine rotor. The test case configuration, I implement a uniform inlet condition of 9 meters per second, which corresponds to a tip speed ratio of 4.2. So this is the mesh. I meshed only single blade with periodic boundaries. I will show the configuration file later on. So in the mesh, it contains 800,000 cells and 10,000 surface cells. So it is actually quite coarse. So please don't put your expectations too high. Just I want to show you how to run such a application SU2, and I want to talk about some possible improvements. So you can see that, and you can apply these improvements in your own application. So this is the a cross section of mesh on the Z equal 3 meters cross section. So you can see that we have some boundary layers around the surface, but the initial first cell height is not sufficient. We have 0.5 millimeters, and we get a Y plus around 25. There are also some locally higher regions, but mostly we have Y plus around 20-25. So this is the surface mesh, and the boundaries extend 5 dimensions away from the blade for the inlet and the side boundaries, and 50 dimensions away for the outlet. So this is some cross sections as well. We have Y equals 0 cross section. As you can see, we have finer mesh around the rotor and also just above a bit rotor. So this is to resolve tip vortices, but you see that it's not sufficient enough. So we need finer meshes. So we will share this both mesh and the configuration file with you after the presentation. And also we have the X is equal to 0, and this should be 3D, by the way. X is equal to 3D cross sections. So again, we have finer mesh around the rotor and coarser through the boundaries. So I actually did 3 simulations. I will show the configuration files each. So we have a half single blade configuration with rigid mesh motion and a full configuration. So I just rotate the mesh 180 degrees to get a full mesh. And this time we do not have any periodic boundary conditions. So I ran the simulation with 16 cores on Truba. So for the half configuration, it took around 10 hours and full took 20 hours for a 4 seconds of physical time simulation. So it corresponds approximately 5 revolution. And also I did again half single blade configuration with a rotating frame. So this is a steady simulation. So this is not sufficient, I know, but for such a convergence criteria, it ran for 12,000 iterations, and it took 2 hours of computational time on 16 cores. So now we can look at the configuration file. So let me change my sharing screen. Okay, so I connected earlier before the presentation Truba. So I have both the mesh file. So let me open the mesh file.
Can you increase the size of the text?
Yeah, sure.
Thank you.
Okay, so let's make it bigger. So I think this should be sufficient.
Yes, thank you.
Okay. So this is actually the mesh file. So it indicates the dimensions, 3 dimensions. So it has the number of elements. So this 14 indicates the shape of each cell, and also we have numbers related to connectivity as well. Also at the end, we should have some, let's say that inlet. So we have, again, some marker text related to boundaries below. So let's first look at the half configuration with rigid motion. So we indicated the solver as well. By the way, this is version 7.3. So the latest version is 7.4. So this is the previous one. So we indicate solver as RANs. I did simulation with SSD turbulence models. We have turbulence intensity, but I commented out. This is not important for the simulation because I did not include any transition models because my Y plus parameter is quite high. We have a direct map problem. We can use edge joint as well here. If you want to do an optimization, you can use the edge joint solver of SU2. I indicated that we have an unsteady simulation with a time step of 0.003 seconds. We have the Mach number angle of attack. So these are some fundamental settings. Again, the reference moment, we have a reference length as rotor diameter, reference area. In boundary conditions, we have the heat flux for wall 1, which corresponds to the rotor blade. So since I have a single rotor blade, I have one marker here. I have the outlets. I indicate, again, the inlet type as mass flow. I did not put any specific inlet profile. Also, I have the inlets. And also here is the periodic boundary condition. So I indicated the boundary conditions, symmetry L and symmetry R. So this is left and right. And there's a 180 degree of periodicity in between them. And also we have this dynamic mesh. So I put rigid motion. As I said earlier, this is dynamic, physically moves the mesh. So since I only have the blades, I do not have to put 2 different configuration files. That's why I can move the whole mesh without any problems. So I put Mach motion origin, and also I have a rotation rate. This corresponds to 72 RPM in minus X axis. I plot the results of the turbine blade of the wall. Also, I have some common parameters, numerical methods, CFR number. I put it as low as possible to get a good convergence. So you could put it higher if you have a high quality mesh. We have the linear solver options. So you can, investigate how this how the settings affect your result from the SU2 documentation. So we have the convergence parameters I do, and 50 inner iteration, and a total of 3000 outer time iteration, but I put maximum time 10 seconds. So I think this one corresponds to the lower one, as I remember. So we indicated input outputs. We indicated the mesh file name format, and also you can change the output writing frequency. So we have the restart, parallel volume result, and surface result. So you can change their writing frequency. For example, in this case, I told SU2 to write the restart files less frequently compared to the other flow results. And also to see how the SU2 performs related to computation time, you have to enable this WRT performance option. What else? Also, we have the outputs over here. As I told you earlier, you can look into the possible outputs with this command. So we have we had rotating frame, vortex identification, etc. And also we can see the Npi results. So for others one, I will show them very quickly. So we do not have any periodic here because we have a full mesh in the full configuration. So I commented out here, but the remainings are the same. And for the reference frame case, again, I have a single blade, again, periodic boundary conditions. Let me go down. So the inlets, the boundary conditions are the same, but so I skipped it. But I put time domain. I switched off the time domain, so I did a steady simulation with this reference frame option. So this is the grid moment changes the rotating frame, as you can see, but the remainings are the similar. So but just differently, we indicate the maximum iteration with iter option here. And also, I want to show you the batch file. Of course, there's a sample file in the Turbo documentation. You can take that. So I just take the module loads from this file, and then I did an MPI run with 16 number of processors. And I compiled the SU2 file in my home directory. And also there's an already compiled one in the Turbo files. So you can either compile yourself or use it the ones in the Turbo files. But I usually compile it myself, to cache the latest capabilities. Okay, so now I showed you the configuration files. So let's look at some results. So let's go back to ParaView. So we get some ParaView files. So this is the volume flow results. So I took the last one. Let me just change the background. Okay, so let's look at from X. So this is not, as you can see, half configuration. So if we use this transform filter in the ParaView, we can rotate it 180 degrees and get the rotated part, and we can open it, the original file, so we can get the whole configuration as a full, but we only simulate the half one. Then we can just take slices to see the results. So let's take it from the rotor plane. So let me take slice as well. So let me close the plane. So we have the wind turbine rotor over here. So if we, let's say that we want to look at the momentum X, let's open it here as well. Let's select that so we can see, oops, I forget, two-dimensional. So you can, see the results over here. Also, you can open the whole volume flow results. Since this is an unsteady simulation, you can play them from the toolbar over here. But I just take the last one to show you the results. Okay, so we are almost running out of time. So also we can, from parallel, we can see the change of the global parameters. So let me open a line chart view. So I open the history file. So it contains change of results with iterations like we have CD, CL. In our case, we have the torque coefficient, thrust coefficient. So for example, we open CQ, torque coefficient. So it's since this is an simulation and single blade oscillates, as you can see, and we can say that the simulation time is not sufficient. We have to simulate it longer. And also we have the CT here as well. So let me go back to the presentation. So we check the output file. So we have the history file. As I told you earlier, we have a variation of residues, force coefficient, moment coefficients, rotating frame coefficients, etc. We have the volume flow results as a preview file. You can also take it as a tech plot file. We have the surface flow results. And also you can take the forces breakdown file, which shows how the force and moment change with each surfaces markers. For example, in the fault configuration, I have two different volts, vol 1 and vol 2. So I can see how forces, I can see the forces as differently, how the first turbine blades experience which forces it sees, and the second one separately. So actually, this is the results of different cases. So on the left side, we have the single blade with rigid motion. In the middle, we have the rigid motion 2 blades. And right-hand side, we have the reference frame with single blade. So for the single blade cases, I just rotated the whole volume and take the results of the case. So this left and right sides are actually symmetrical, as you can see. But we see that the results of the single blade and 2 blade combinations are quite similar. So I want to show you this because of that, the periodic boundary condition I told you earlier, but the results are quite different in the reference frame. So this could be due to the lack of convergence, but mostly if you look into literature, you see that the results of rigid motion and reference frame differ. So what could be the possible improvements? So first of all, we might have a shorter first cell height to get a lower Y plus, because we know that we have separation and complex flow interaction. So this is important. If not, you can implement the Wolf function and check that. We could include a transition model. I did that in my simulation, but you can do it yourself to capture the laminar flow and laminar turbulent transition. We could include remaining rotor components, but it would add complexity. We could add atmospheric boundary layer with a non-uniform net velocity profile, which we can with SU2. If you want to do a validation against an experimental data, you have to include wind tunnel walls as well. If you're not, you may lose some accuracy. So this is an NRL phase 6. This is a small wind turbine. It has many wind tunnel experimental results. So you may do some validation with that. And also, of course, we could add some finer mesh around the blade to preserve the turbine structure. So I did not show it, the vorticity, because we have limited time. But if you want, you can run the simulation and see that where we lost that vorticity, the realistic vorticity. So that's why I want to show you some coarse mesh and to see possible improvements. Okay, so this was the end of my presentation. Thank you for your attention and patience. If you have any questions, I can answer them.
Okay, thank you, Ata, for this great presentation. Applications were really helpful. I think we have some questions. We can go over them. I will read them. For small wind turbine, 2 kilowatts analysis, do you suggest to include nacelle?
Well, as I said earlier, it depends on your application, but mostly for that kind of small wind turbines, they are used for wind tunnel experiments, not, of course, for nowadays, not for energy production. So mostly we see some power production curve for such turbines. So if your case is to see the power production, then you may not model the nacelle. But if you want to look at the wake and etc., you may include the nacelle. And also you can look at the literature whether such wind turbine results to see whether the nacelle affects the results. So literature could be really helpful before you prepare all your CFD configuration.
Also, maybe I can mention there are these test cases or blind test cases, validation cases in the literature. And in RUZGEM also we do experimental measurements to have such validation test cases to compare our CFD results with the experimental measurements. It's important to validate your methodology, your grid and numerical methods that you choose. If to be aware of how accurate can you simulate, and then you can continue with your analysis after that. Thank you. Second question, could we define automatic mesh, for example, fine and high resolution? What was the element sizes?
What do you mean by automatic mesh? I didn't get that. So I did the mesh with pointwise T-Rex function.
Mm-hmm.
But of course, you can get a finer mesh with different parameters, such an automatic mesh. But I think I couldn't get the question right.
Yeah, well, maybe I can comment. Mesh generation is never automatic. I mean, user experience is really important, and you need to play with your mesh to get the fine or suitable meshes. I mean, if someone is using automatic just sources, some parameters, you need to still play with them until you get nice mesh. So user experience, and it takes time. Maybe third of the time of a CFD simulation is mesh generation. So we can say that.
That's why I wanted to emphasize about the interaction with non-turbine components. So if you add this nacelle, then it will more time.
Yeah. So Ata here specifically showed you a coarse mesh. So there are lots of improvements that needs to be done, right? But you start with a coarse mesh, and then you see that your solution, your methodology is working correctly, and then you can improve your mesh. You can play with your numerical method parameters, etc., until you get a nice validation or nice results. Yeah. Okay. Any comments, Ata?
No, that's perfect.
Okay. Can you perform wind tunnel tests and compare your computational results and findings with the wind tunnel test results and findings? We already said that. Yes. In RUZGEM, yes, we are doing wind tunnel tests. There are experimentalists, aerodynamicists, faculty members and graduate students, and also researchers working at RUZGEM. They are doing tests, and they are available in the literature as well. So can you get feedbacks from wind power plants and validate your results and findings in your wind tunnel tests, if any, and computational results and findings, if any, real life related studies? Yeah, that's a good question as well. Recently, there was one, maybe I can say that master thesis completed. They tried to simulate wind farms, wind farm modeling, and they used real wind farm data to compare their results. So it was a nice thesis study, actually. So yeah, we do, if available in similar cases, we can do such studies. Yeah. It is important to have real data. Can we make analysis for twin rotor wind turbine with using SU2?
So
yeah.
if you have a good mesh, of course you can.
Yes.
But it's hard work, not just one or two rotors.
So, for example, you had this one rotor domain, right? If you can have a one rotor domain, and on top of it, you can have another domain, right? This inner circle. Do you have it?
Yeah, something like that. So,
so you can have two domains, two counter-rotating domains. So you can give rotational speeds differently to those two domains. You can have 4 rotors, 16 rotors. You can actually simulate eVTOLs yeah, it's all possible, of course. Next question. Does forces breakdown show relationship between relativity velocity around the blade and wind velocity already? Okay, so you are asking about the relative velocity and wind velocity and force calculations, the effect on the force?
I think it does not. It calculates the forces with the motion parameters. So where was it? It calculates the forces with this number. So
you mean, is it used for non-dimensionalization?
Yeah.
Okay.
As I know, it does not.
Okay. Can you perform, or did we read this? Yes, we already read this one. Thank you. Does SU2 have an incompressible solver?
Yes, it does. Let me show you. Okay, so these are all solver types. So we have this ink, obvious ink, earlier Navier-Stokes rounds. They are all incompressible.
Yes, you can select different types of solvers here. Yes. LES and DES also, right? Maybe not in, is it in this version or a different? I mean, there are in the literature, there are DES.
There's DES in this version, yeah. I'm not sure about LES. I think there's LES, but I don't know whether it is a finite volume method, but there's DES.
Okay. Finer mesh. What was that?
It was related to an earlier question about automatic mesh generation.
Automatic mesh generation. Yeah, you cannot get the fine mesh automatically, right? Can you? I mean, is it? Do we have adaptive mesh in SU2? Maybe that's if that is the question.
As I know, no. It has mesh deformation, but not adaptation.
Okay, so you can have deformed meshes, so remeshing or deforming the mesh, not remeshing. If it has remeshing, maybe it can do adaptation as well. I'm not sure. Maybe somebody is already working on it. Yeah. Okay. Which one of the simulations would be considered more correct between rigid body motion and reference frame motion? What is the advantages of using the one or the other?
Well, as I know, in literature, rigid motion simulations are considered to be more accurate, but the difference is actually apparent. So it relates to the computational time. It has a huge difference.
Yeah,
but,
if you have enough accuracy with the reference frame, and if you need that steady state solution, you can have in shorter time, right? You can have a solution in a shorter time. But if you need more accuracy or more unsteady complex interactions, you need the rigid body motion. Right.
There are various papers in the literature, so there are researchers that looked at the differences between these two approaches, so you can find it on the internet.
Thank you. I wonder how results differ from experimental results and also from the commercial softwares, not specifically for this application, but in general, according to your experience. This is a very general question. It depends on the problems. I mean, any CFD solver, let's say commercial solver and open source CFD solvers using the same methodology, same governing equations, same grids, you expect to get similar results. Maybe algorithms or writing, programming, some, how can I say, computer errors significant digit errors you can have, I guess. If everything is same, you should have the same solution. But usually there might be some differences in the methodologies or writing the code. So there are usually some differences between the different solvers trying to solve the same problem. So it's hard to compare them. I mean, it's easy to compare them, but so if there's any validation case, experimental results, you can always compare, of course, with the experiments. But even for wind turbine rotor cases, let's say, these blind test cases, if you look at the literature for blind test cases, many different research groups try to solve the same problem, and they all have different results. Wake characteristics, they all have different. So it's really hard to say which one is correct. Thank you. Vibrational effects on analysis, especially in CFD, is it important?
I think it's more important in structurally, not in aerodynamically.
Even aeroelastic interactions, maybe? If the blade is deforming?
I mean, in which scale of vibration? Small or, if really high deflection, of course it's important, but in small scale, I think in aerodynamic point of view, it is not that much important.
Yeah, we can assume rigid blades, rigid motions, so we have enough accuracy. But if you have more accuracy, you may need to model aeroelastic deformations as well, if that's what you mean. Yeah. Volumetric mesh insights can be helpful for twin modeling, in my opinion. You mean twin rotors? For twin rotors, you will have, instead of one rotor, you will have two rotors, but there will be a space between them, right? So your mesh you need to create a nice mesh between them so that you can capture the interactions. So finer mesh you may need around both rotors, actually. Ata?
Well, I think there are lots of applications in helicopter CFD related to this twin modeling, but they're in high speed. So, but yeah, there could be implementations between them. So yeah, it's possible, but it's hard work.
Mm-hmm. Yeah, the difference is that's a good point. For helicopter rotors or propellers, they have high rotational speed compared to wind turbines. Wind turbines have really low rotational speed. So 5 revolutions, you can easily compute and you can get the wake developed and you have a nice power estimation, let's say. But for helicopter rotors, with 5 revolutions, your wake will not go away. So it will not be enough. You need more revolutions and it's so fast. So your time step will be so small. So it's really difficult to do unsteady simulations. In those cases, we can say that it will be expensive. Yeah, real-time simulations. Okay. Do you know we can couple this multi-zone solver with structural solver of SU2 to obtain an FSI simulation with deformations? Maybe can we do that?
Well, as I know, there are works with SU2. There are you can check SU2 conference papers. So I believe there are some works of FSI simulation, but no, I'm not expert, so I have no idea.
Yeah, maybe small changes with mesh deformation might be possible. Yeah, I remember those kind of papers as well, but we haven't tried it yet. Thank you. Computer speed is always important, yes. Okay, I think we are done with the questions. Thank you, everyone. Thank you, Ata. So we will have lunch break and then let me check. We will meet 13:15, right? 13:15 after 45 minutes. After the lunch, we will meet again. So see you all. Bye. Merhabalar. Merhaba herkese. Hello. Elif hocam burada mısınız? Are you here?
Yes, I'm here.
Yes. Okay, great. Thank you. Maybe we can start. So I will introduce. Hello everyone. So in the afternoon, we are meeting again to continue with the introduction to offshore wind turbines and design aspects also by Associate Professor Dr. Elif Oğuz from Civil Engineering Department. We are also working together at RUZGEM. So she will give an introduction and lots of terminologies. If you are new into this area, hopefully it will be helpful. Elif hocam, it's your turn. Thank you.
Thank you very much, Nilay hocam. Let me share my screen now. I will use microphone from somewhere else. So now, can you see my screen? Okay,
yes, we can.
I think it's coming, right? Okay.
Mm-hmm.
Okay, so thank you very much. Good afternoon, everyone. Welcome to our workshop on wind energy computational analysis. I hope that you have enjoyed so far. And in the afternoon, as Nilay hocam mentioned, we will make an introduction to offshore wind turbine design. And right after me, our research assistant, Putra, will be talking about the aerodynamic and hydrodynamic analysis of offshore wind turbines. And after that, we will have also another important session today. You will have introduction to wake models and wind farm analysis, and also wind farm safety analysis will be shown to you. So here, let's talk about the introduction to offshore wind turbines. Here you see the outline of my presentation today. I will give a brief introduction to offshore wind, and then I will talk about the classification of offshore wind turbines today by mentioning their design aspects and stability conditions, which are quite important when we are designing all those. And then I will talk about the numerical modeling of offshore wind turbines, including performance analysis of such systems, what kind of tests we should have to evaluate their performances under real sea conditions. And finally, before I leave the floor to Putra, I will mention recent developments in offshore wind industry. So here, let me start with the new onshore and offshore installations in Europe in 2020. In this figure, you see new onshore and offshore installations in Europe. As you see in 2020, it was the date when the pandemic started. Here, the light blues indicates the offshore installations, while dark blue shows the onshore installations, basically onshore counterpart. We can see here the installations of offshore was high in Netherlands and followed by actually Belgium, the UK, and the Germany. And still we can see there is a continuous trend in land-based installations. So here in this slide, we can see offshore wind farm foundations worldwide. This is quite important, I think. As you see, offshore developments mainly is leading by Europe. And when we have a look at the distributions in Europe, we can see 70% of those structures are monopile, which is a fixed bottom offshore wind turbines. And there are some other percentage, and also others indicated as 3% here. This is for floating wind turbines. And when we have a look at the Asia, actually, you can still see there are some applications on monopiles, but we can see also other types as well, like high-rise pile cap having a 40%. Actually, here I should mention one of the most important parameters when we are selecting a foundation type or floating type is the soil condition. So depending on the geographical conditions and sea bottom conditions, water depth, we can select different types. But in general, as you see all over the world, when we have a look at the foundations and the wind farms, actually we can realize that monopiles are commonly used foundation types in offshore so far. So you can expect that they are commercialized. But we will be talking about the 3% here today, most of the time. So why? Let me talk about the importance of offshore. Why do we need to move on to offshore installations? Let's review the advantages and disadvantages of all systems, because each renewable energy system has significant advantages and disadvantages. As you know, a large number of land-based installations have been constructed in order to convert wind energy into electricity. And these are very handy actually in terms of cost, maintenance. You can easily go there and do the maintenance job. And also it is quite common to connect the existing grids actually. But there are some disadvantages. These land-based wind farms have some negative environmental effects such as noise or visual impact or some drawbacks for bird life. Also, as you see here, the components, they have got big components, so transportation of such components are very difficult. So for these reasons, many energy suppliers started to invest in offshore wind farms. And so the developments were started with the fixed bottom offshore wind turbines, because again, they are located near the shore actually. So maintenance and grid connection is easy compared to floating types. But the thing is, although fixed offshore wind farms are becoming very, famous and numerous around the coast of the UK, Germany and Denmark, they are constrained by one very important factor. This is water depth. Because when we have a look at the other countries, for many countries actually, fixed bottom offshore winds is not an option, because the continental shelf drops away suddenly and steeply, making the installation of those systems are very difficult. And sometimes actually impossible than the waters in the Northern Europe. And also, when we have a look at the fixed type offshore wind turbines, they are becoming expensive after 50 meters water depth, and they are not practical to deployment actually. So when we compare with the land-based and the offshore fixed turbines, deep water floating wind turbines have many benefits, such as capturing a more stable wind field with higher average velocities. So what does it mean? Basically, since the wind power is proportional to the cube of the wind velocity, even we have a small increase in the mean wind velocity, it significantly increases the system efficiency. And also, compared to land-based counterparts, relatively low surface roughness of the ocean gives rise to higher wind speeds than those found on land. So we can say floating offshore wind turbine concepts are one of the most promising renewable energy systems in order to generate electricity in the near future. But of course, we should keep in our mind that offshore floating wind turbines have some drawbacks as well. The cost of such systems are still actually high for floating concepts, and there are a number of projects currently they are running in order to reduce their costs. And grid connection requires extra cable. Sometimes offshore substations actually might be required as well, so which end up with extra cost here. And due to the harsh environment that our structure will have to be survived, having a small dynamic response of the system becomes a challenging issue for such systems. And here also, I would like to talk about the recent trends of the wind turbine sizes and capacity. When we have a look at the trends of the wind turbines, we can see an increasing trend. As you see here, the turbine capacity was 0.5 megawatts in 1990s, and current wind turbines have more than 5 megawatts capacity. And what kind of studies can be carried out in this field? In recent years, many studies actually carried out to investigate the performance of the floating offshore wind turbine with different turbine capacities. And some of the studies also aim to improve the turbine capacity for the same floater concept. And some others aim to improve the hydrodynamic performance of the system. And since floating offshore wind turbine systems have to be designed for each pilot area, considering the environmental conditions like metocean data, wind, currents, and wind wave. So the solution all the time, most of the time, is unique. So for this reason, many optimization studies were performed to determine the most feasible option for a selected region. And when we have a look at the installations, actually, here, we can see the average water depth was around 16 meters in 2013, and it reached to 33 meters in 2019. And similarly, when we have a look at the distance to shore values, we can see offshore wind farm deployments have a distance of 39 kilometers to shore in 2013. And recently, we can see some of the deployments, they are 60 kilometers away from the shore. So what does it mean? This shows the continuous developments in offshore wind industry. And similarly, actually, when we have a look at the water depths of the installations, we can realize that the majority of the deployments were performed in the water depths smaller than 40 meters. And only 4% of the deployments were in the water depths greater than 40 meters. And today we will be discussing all those systems. Now let's move on to discuss offshore wind turbines. Basically, offshore wind turbines can be divided into two groups as fixed bottom offshore wind turbines and floating offshore wind turbines. So here on the left-hand side of this figure, you see some of the examples of fixed bottom offshore wind turbines. So the very first one is the commonly used one all over the world, as I mentioned before, monopile. Tripod, jacket type, suction bucket type, and gravity base can be listed also within this group. And we can deploy fixed bottom wind turbines up to 50 meters or sometimes 60 meters water depth, but they cannot be economical and practical for the water depths greater than this value, 60 meters, let's say. On the right-hand side of the figure, as you see some of the examples for offshore floating wind turbine concepts, the very first one is known as parboard system, which is a ballast stabilized system with catenary mooring lines. And in the middle of the right-hand side, you see mooring line stabilized system, which is known as the tension leg platform. And the last one is known as the barge, which can be stabilized by buoyancy and water plane area. We will discuss this one today. And it has a catenary mooring lines, which means that they are slack. So here, I would like to show you here the platform cost relation with respect to support technology that we have, okay? So basically, when we have a look at the gravity-based systems and monopile systems, they are economic for the water depths smaller than 30 meters. But as I said, there are some applications for 40 meters as well, for example. Depending on the other criteria, we may have some different applications. But in general, we can definitely say gravity-based systems and monopiles are fully economic up to a water depth of 30 meters. And tripod and jacket systems can be also another alternative for the transitional water depths. And for the water depths greater than 70 meters, floating concepts might be solution for our problem. So before we continue, actually, I would like to give an introduction to offshore wind because offshore wind, when we say offshore wind, we should remember that this borrows from two industries. One is the offshore oil and gas sector that has been building floating platforms to reach deeper waters since 1950s. And the other one is the onshore wind technologies. So offshore wind actually tries to integrate these experiences in order to develop efficient systems to serve energy extraction in offshore in the sea. And here in this process, actually the platform type has a very important role, has a definitory role, because it adds extra degrees of freedom that are not encountered onshore. So what I mean here, actually it adds definitely lateral and rotational motions at the turbine's base. So the related motions and also the accelerations then affect the turbine's performance and its safety. So it is quite important to understand the platform types and the advantages and disadvantages of each system because there is a direct relation with their design and stability issues. Also, we can say it is possible to say that there are several changes when going from offshore oil and gas to offshore wind platforms. The reason is here, it is possible to build larger platforms, for oil and gas, because a single platform can operate for long years in an offshore field, in the oil field, and extracting, high volumes of fossil-based fuels. But the central issue when we have a look at the offshore wind, actually, it is the economics, right? So no matter how large, a single turbine is always insufficient, providing a significant amount of power. Actually, this is not the rule that we are putting place. This limitation is due to the Betz law, which relates the maximum energy extracted to the area swept by the blades. So offshore wind platforms are designed with the idea that they will be installed in huge numbers, like wind farms, as you know. So here, consideration of two sectors, oil and gas and onshore turbine technologies, we have an understanding of offshore wind. So right now, you can imagine easier production of such systems, smaller hull systems, minimal effect on turbine dynamics, easy transport and installation, and also easier decommissioning are very crucial actually for offshore wind. And now, let me talk briefly about the identification of environmental loads on floating wind turbines. As you can imagine, a floating wind turbine faces aerodynamic and hydrodynamic loads. And in response here, its dynamics are affected by its hull form, platform form, size, and their mooring setup. So here, let me show you the equation of motion of a floater. Actually, we can write it down like that. So we have aerodynamic force and hydrodynamic force on the left-hand side of this equation. And here, the aerodynamic component, actually, we can divide into two groups. First group, the presence of a large tower. For example, if we consider DTU's 10 megawatt turbine, this tower stands like 129 meters high, and the rotor with the blades can reach over like 80 meters. So this itself presents a drag load, even without running a turbine. This is the first aerodynamic load that we have to encounter. And this scenario is always present actually, because this needs to be considered for extreme conditions as well, and also transportation. But on the other hand, we have to consider the operational condition of the turbine, because at the end of the day, we have to yield some energy from wind. So in this case, the turbine will generate a significant thrust on the tower, which acts as a lever, so resulting in associating pitching moments, okay? So the hydrodynamic force here, when we have a look at the hydrodynamic force, actually, here, these are mainly the currents and the wave loads. And there are several methods to calculate wave loading on an offshore structure. So we can use Morrison equation if your structure is slender enough. And you can use panel methods, or you can use computational fluid dynamics. I will not go into detail, but I will just mention some of the important things here. Here, the size of the platform in comparison to encountered wavelength plays an important role when we are selecting the suitable solution method. So here, as the turbines get larger, for our case, here the structure that supports them increase in size as well. So if you have 5 megawatt or 10 megawatt, so in order to deploy such big turbines, your platform will increase as well. The size of the platform will increase as well. So for this reason, our structures are generally large enough to deflect the incoming waves and require a panel method solution. But on the other hand, if we consider the smaller components, like connecting the braces of some structures or some of the pontoons that we consider, these structures can be treated as transparent structures that they do not deflect the waves. If it is the case, we can apply Morrison equation actually to calculate the wave loads. On the right-hand side of the equation, that we have inertial components, damping and restoring forces. Out of these components, the restoring part of the equation, basically here CH and CM, can vary significantly between the platform types. I will talk in a minute. And the viscous damping is another component actually that becomes less prevalent in some cases. So here, after defining the loads, that brings the equation, question of how to counteract these forces, because our structure will have to deal with those forces, and it has to be stable. So actually, it is possible to classify all platforms into 4 primary types. As you see here, you can see some of the examples from oil and gas, actually. From A to D, you see semi-submersible, TLP, spar, and the barge system. So here, actually, they are classified into these categories by the flotation principle. Instead of by looking at their geometries or hull shape, we categorize them actually by looking at their flotation principles. In other words, their stability condition. So for example, when we have a look at the semi-submersible and the tension leg platform A and B, they are looking similar, right? Visually similar, but they are not the same structures. So this was an example from oil and gas. You see the size of the structures and you know how many things that we need to also consider on board. But when we have a look at the offshore wind turbines for the platforms actually, so let's see what kind of things we need to consider. In offshore wind, variations of these hull forms from offshore oil and gas can be used as well, but the deck space required for oil and gas processing and also storage reduces the hosting a tower and turbine, because we will have only tower and turbine on it. We don't require to host any other gas processing or storage systems. And there is also no need for accommodation area. So the turbines operate without onboard personnel. As you know, you can remotely run those systems. So these considerations lead to smaller hull systems, as you see here in the examples. So here the hull forms, on the other hand, vary very significantly. For example, this figure shows the outcome of one of the important study in the literature, namely Deep Sea Consortium. And at the end, E figure named as E indicates that the Santec TLP design. Actually, the Deep Sea Wind Consortium's work is widely used in the research field as the platform and turbine data were publicly available for researchers. So we can use all those. But these designs were made for 5 megawatts turbines. So on these days, since our focus is increased to 10 megawatts, 15 megawatts, actually it is for validation purposes, of course, still can be used. But the Santec TLP here, on the other hand, is made for the 10 megawatt DTU's turbine. Okay, so right now, I think we can continue with the classification of floating offshore wind turbines. Offshore floating platforms, what we have said, can be classified based on their methods of attaining stability. And we can place them on a stability triangle, which is defined by National Renewable Energy Laboratory in 2007. On the left-hand side, you see this figure shows the position of each alternative and as a function of their principal stability method. But in practice, we should keep in our minds that all platform types make use of 3 principles that I will talk about it in a minute. But the categorization always focuses on the primary contributor for stability. So on the right-hand side, you see again some of the examples. The very first one is an example for barge and spar, as you see, and TLP from an experimental stuff, and also semi-submersible. So now let's talk about the first one. The first classification is known as the water plane area stabilized platforms. And in some of the books, you can see as buoy stabilized as well. Water plane area stabilized platforms actually are the most closely related to ships. Their principle is same. So the principle of a barge wind platform exactly resembles that of the barge transport vessel. So both are classified as having low draft and large water plane area to create large hydrostatic restoring moments. And as you see here on the figure on the left-hand side, this is a representation of ITI barge system. So we can see the hull's prismatic form here and having a low draft. As you see, this hull form has a large exposed area to wave forces. And also it can show adverse pitching motion that affect the turbine's performance. And this type of platform is moved using catenary lines, which means its motions are not restricted at all. And also some of the cases in the barge, we may have some corrosion problem. So because water plane area can be large for these systems. And the second example, actually, the classic example of a deep draft stabilized platform is known as single point anchor reservoir. In abbreviation, we call them SPAR. As you see here on the figure, SPAR resembles exactly as a cylinder. So the idea of a SPAR is to add sufficient weight at a deep enough location so that the center of gravity can be lowered below the center of buoyancy. So this type signifies that the structure needs a significant draft. So we can actually reach like 120 meters water depth for a 5 megawatt wind turbine. And in terms of like shortcomings of this type, the hull form, as you see here, like a cylinder, so it is so simple. And due to this simplicity, it is somewhat transparent to waves due to its small water plane area. And this type shows limited lateral motion, such as surging in X direction. And it is easier to produce, actually. Another advantage of such system can be listed as it is easier to produce compared to other alternatives, because as you see, generally it has just only one main column. But due to this simplicity, it encounters vortex-induced vibrations as the cylinder heaves, which means that in the vertical direction, if it oscillates, then it creates some vortices and that lead to low frequency vibrations, which is very dangerous. And actually this may lead to fatigue loss in long term. And this problem can be solved using some strakes, some helical strakes. Okay, so now let's continue with the other type. Tension lag platforms. In abbreviation, we can show them as TLPs. They are stabilized by a combination of mooring lines, as you see here, pretension mooring lines, and the buoyancy forces. So basically, these structures are not made to be stable and cannot float without their mooring lines. So what is the principle? Actually, here, the principle of the TLP is that it has higher buoyancy than mass, and it causes an upward force. So it pins the structure up. So this force can be balanced by the mooring lines that are always in tension, which stabilizes the structure. And commonly, they are connected to the seabeds using pies. But of course, the seabed at the installation area should allow this connection. So this system cannot be deployed for everywhere. For example, a soft soil that cannot respond to the loads in the piles would not allow the installation of a tension lag platform. And also an alternative to piles can be the use of gravity anchors. There are some studies recently, use of gravity anchors for TLPs. And due to the tension of the lines, actually, we can think that TLP resembles like as a fixed structure. And they are measured in centimeters, actually, in the modes that are restricted. This restriction provides a stable platform for the turbine to operate. So in terms of dynamic response, actually TLP provides us an advantage like that. But on the other hand, even with motions in centimeters, the lines can lose their tension. So we name it as like wing slag. And when they come back into tension, they cause a high dynamic load that may even lead to the loss of the structure. So their motions need to be carefully evaluated. For TLP, it is quite important that you can lose your structure stability by losing the tensions. Another type here is known as semi-submersibles, and they are listed as column stabilized units by BMV, which is one of the important classification society in offshore wind structures and offshore structures. So the reason for this classification actually is that they use two principles from barge and from a spar. So in operational modes, their water plane area is not as large as barge, so its draft also is not low either. And this platform has several advantages. What else? For example, it does not rely on the soil pile connection as a TLP, and it does not show more significant motions of the barge due to exposure to hydrodynamic forces. So they can be preferred for their stability. And they can be also towed to the installation location with the turbine installed, as long as the transport draft is lower what the port allows. So you can actually mount everything on the shore and then in the port, and then you can tow to the installation area. This might be an advantage. But there is a drawback of this platform, which is the complexity in its production compared to spar, and also it is heavier than a TLP, and it uses also capillary mooring lines, so it does not have the minimum response of a TLP in its restricted modes. Okay, so up to this point, I have introduced the platform types and their stability principles and fundamental characteristics. Now, I would like to continue with the resonance characteristics. In ISSC 2012, it defines the dynamics of these platform types by classifying their motions into restricted and compliant modes, as you see here, with capital C and R. And you see the platform types on the left-hand side, which we have just reviewed, and their stability methods. And search and sway, these are the lateral motions of the platform. Heave, this is the lateral motions in vertical direction. Roll and pitch, and yaw, they are the rotational motions. And here, once we know the principles, actually it becomes a matter of adapting the correct platform shape, hull shape, in order to meet the requirements regarding their dynamics. So here in this table, as you see, this table shows each platform's responses in all modes, either by capital C, compliance, or restriction with capital R. Restricted modes with limited motions are shown with R, while C represents the compliance. So here, when we have a look at this table, we can say TLP identifies itself by restricted heave and pitch motions. As you see here, we have two R's in heave and pitch motions. So how small the motions will be in the restricted modes will depend on the structure. So now let's talk a little bit more about this one, because this is quite important in terms of the structure's dynamic and stability, whether it will survive for the design conditions. Here, the type of restriction that we have mentioned also reflects in terms of resonance characteristics of each platform type. So here you see in this table TLP, spar-bore, and semi-submersible from one of the deep sea wind consortium again, this figure. And you see the natural periods on the left-hand side on the y-axis and 6 degrees of motion on the x-axis. So here, actually our platforms are designed to avoid the first order excitation frequency of the 5 to 25 seconds range. This is quite important because the periods towards 25 seconds reflect a storm condition and the waves smaller than 5 seconds are generally too small to force a structure into motion. So the platforms can be designed in order to avoid the range between these values. So what we are doing basically when we are designing those structures, basically the method of doing is a function of compliance or restriction of the system in each mode. So as a general principle, in the compliance mode, the idea is to allow the platform to have resonant periods longer than 25 seconds. And in the restricted mode, this value is to be dropped below 5 seconds. So here, as I said earlier, we see a comparison of 3 platforms' natural periods from Deep Sea Wind Consortium. And it can be seen here on the table. TLP has the shortest search periods, right here. And what does it mean actually? Because this is lowering the value is caused by the shorter mooring lines that cause direct interaction with the motions of the platform. So after reaching a searching limit, the tensions in the mooring lines revert the structure to its position like a pendulum. And TLPs are intended to be deep water structures. If you see in the oil and gas sector, they are designed for 1,000 meters water depth. So installing them below a certain depth actually may put them into search resonance. And here clearly shows the restricted mode of the TLPs, and as its resonance frequency is quite high. And the other structures tend also towards the upper end of the wave periods. For example, when we have a look at the semi-submersible here, it has a value of 17.5 seconds, and it may end up with resonance in a storm case. Actually here, ideally, it should be adjusted by lowering the water plane area and making the structure less stiff. But in the deep sea wind structures in this consortium, these structures are not optimized designs for research purposes. So this outcome can be accepted. But when we are designing, as I mentioned, we should really be careful whether our structures, natural frequencies are in those ranges or not. So now, of course, we talk about in the morning the aerodynamics, and then now I introduce you the floating systems. Now, of course, we have to also consider the mooring systems used in offshore platforms. Now, let me introduce mooring systems used in offshore platforms briefly. Here, actually, most of the platform types can be moored using catenary lines, as you see here on the left-hand side and on the in the middle, because this is the simplest one, and most platforms are can be moored using catenary lines of various materials and also configurations. But a platform's mooring setup may involve several scenarios. In the simple case, the line may be made from a single material, for example, and tension between the soil and the structure, vertically positioned. If it is the case, we name it as taut mooring lines, as you see on the right-hand side. And this is for TLP structures. And the single material option is generally the case for a TLP. In the oil and gas sector, these lines are generally hollow steel pipes. And in this scenario, they can be termed as tandem. In the case of renewable energy systems, experiments with steel ropes or synthetic materials can be performed as well over the last decades, actually. There are many experiments using different steel types and synthetic materials. So for this case, it is advantageous to use only one material in order to avoid multiple connections on a structure that is under high tension. So for if you are designing a TLP, you should keep in your mind that it's better to use only one type of material in order not to have any high tension in your system. On the other hand, when we design other systems like using catenary configurations, they can hang freely from the structure and they can be anchored to the seabed. So the freely hanging section may be floating or partially positioned on the seabed. And the restoring force that it provides depends on the position. Unlike tandem mooring lines, catenary moorings always, not always, but may use several materials for different scenarios. And it is also possible to connect buoyancy bodies to the lines to lift certain line sections and modify the moorings behavior. So all in all, we can say all platform types other than the TLP use catenary mooring line systems. So up to this point, actually I tried to summarize the importance and the differences of floating offshore wind turbine concepts in terms of design and the stability issues, since it becomes an extremely important and popular. As I said before, all these structures have to be designed for a specific location because each location includes different wind, wave, and sea bottom condition. So now I would like to continue with the steps that need to be followed for any design using an example, a TLP. So let's remember the TLPs. TLPs actually are very popular structures in deep water offshore oil and gas sector for oil extraction. And they are gaining interest in floating wind energy sectors because of their small dynamic responses compared to other floating platforms, as we discussed. They are restricted in heave and pitch. And TLP also has a potential to offer significantly reduced structural costs due to the reduced steel weight compared to fixed offshore wind turbines. And normally, those structures are designed for 1,000 meters water depths for oil extraction in offshore. But of course, there is a compromise between the distance from the land and the available energy. So when we want to design these structures for relatively shallow water, like 70 meters or 80 meters water depth, it becomes challenging for us, but the novelty starts at this point. So now let's have a look at the basic components of a TLP here. You see piles which are connected to the connected structure to the seabed, and we have tendons, pretensioned mooring lines, as I mentioned before. And we have pontoon elements here. They are the lateral elements, but we don't have to have pontoons each type actually. And, or in this configuration, this is just an example from Iberdrola's patent. And we have a central column here and has a conical transition. Again, the design of TLP might be different. I mean, in terms of geometry, the principles should be same, but we may have different configurations. And we have tower and turbine. And on the right-hand side here, you see the 6 degrees of motions that surge, heave, and sway in transitional motions, and yaw, pitch, and roll in the rotational motions. So here, let me give you a brief description on the numerical modeling of floating offshore wind turbines. After me, Putra will continue and show you some hands-on activities in OpenFast. But what kind of steps we have to follow if we would like to design a floating offshore wind turbine in a numerical environment? I will also combine those, some of the examples using from experimental stuff. So here, if you are a design developer, basically you require a numerical approach at the first stage of design due to time and cost restraints. This is valid for every design. And after obtaining numerical results, of course, we have to carry out some laboratory tests. And then following these small, medium, and full-scale demonstrations are required to be able to commercialize such systems. Since our focus here is on the numerical analysis of wind turbines today, here I would like to summarize the general steps that can be used in numerical analysis of floating offshore wind turbines. So for the beginners, generating a numerical model for a benchmark case is an important step. So you can just choose one of the structures. We have lots of publicly available structures, very well validated structures developed and published by some of the research institutions. So based on the structural similarities, you can select a benchmark case, and then you can start with, creating the geometry of the system, and mesh generation should be performed. And then hydrodynamic analysis should be carried out by using potential flow-based open source codes, might be an alternative such as HAMS, NEMO, or using a hydrodynamic analysis software such as Vomit, ANSYS Fluent, or ANSYS Aqua. And parallel to those calculations, also there is a need to model the aerodynamics of the turbine, and also environmental conditions such as wave, tide, current, or wind conditions as well, wind fields, they should also model considering real sea states. And after that, the output of our hydrodynamics over basically hydrodynamic coefficients of the floater can be used as an input to OpenFAST or FAST, which version that you use, together with aerodynamic results and environmental conditions, and compare the coupled analysis results with the benchmark case. So far, if you model a benchmark case and if you see the validation of your results with this benchmark, then you may try to continue to run some other simulations. And if you design something, so you can also continue with the performance analysis. And also, I will actually maybe skip this slide, as Nilay Hocam mentioned in the morning. What kind of modules in FAST, previously we call it FAST, right now we use OpenFAST. So just let me talk a little bit quickly. We can introduce wind turbine properties, and we can model wind fields using TURBSIM, for example. You can model turbulence or constant wind conditions, and you can just use all those in Aerodyn. And on the other hand, you can also define in OpenFAST like platform properties, wave conditions, and you can use Vomit here, but instead of Vomit, since the Vomit output is can be used in FAST, this is written here, but of course, instead of this, I will show you in a minute what kind of hydrodynamic solvers you can use. And on the other hand, if your focus is on the mooring line properties or mooring line developments, you can also use submodule of FAST. And also there is a connection with OrcaFlex and some other software as well. And then you can calculate and include the mooring statics and dynamics in FAST as well. So at the end of the day, you can analyze your structure considering all the loads that it can face into. So here, I will mainly talk about the hydrodynamic modeling of an offshore floating wind turbine. What we have said previously, Vomit output actually embedded in FAST automatically. Vomit is developed by MIT, but here, since in the recent years, there are many open source codes, you can also use the other alternatives. You see different BAM solvers here and their characteristics. As you see, Vomit is a software developed by MIT. NEMO, it is an open source code which is developed by Nantes Laboratory in France. And actually, this is originally developed for analysis, hydrodynamic analysis of wave energy converters. But there is an option that you can analyze your floating turbine as well. But the output of NIMOC can be converted to the vomit output style, let's say. But recently there is another code, open source code like BEM Rosetta, so you can use the output of NIMOC and convert using BEM Rosetta into the vomit output. And then you can insert into this one to fast or open pass. And there is another tool, namely ANSYS Aqua, that can be used in order to carry out hydrodynamic analysis of all those structures, Aquaplast, VADAM. And finally, we have HAMS here. This is in open version hydrodynamic analysis of marine structures. This is actually released in 2021. So that's why we cannot see its usage here. But the thing is, HAMS, I would like to give brief introduction to HAMS. This is an open source code developed by Leo, and it is based on panel method and based on potential flow theory. And it can build exactly same vomit output style. So here you see on the left-hand side, the coordinate system used in HAMS, and an example mesh, Putra will show you in detail all those. I mean, HAMS performance recently tested so much, and we have been validating this software for different structures. So for the new beginners, if you are interested in hydrodynamic modeling of floating wind turbines, I highly recommend to use HAMS and compare your results with other hydrodynamic models as well. But as we discussed previously, even you model everything exactly the same way, you may have some differences. I will just skip this slide as we have talked about this one earlier, and probably Putra will show you some other simulations, hands-on simulations as well. So now I would like to just give a brief description on what kind of hydrodynamic performance analysis we should carry out to see whether our structure is well designed or not. Here you see an experimental setup of free oscillation test in search direction. Just to visualize, I use this one. So the first thing is carrying out free oscillation tests. Why do we need all those tests? In order to identify the resonance region, which we mentioned earlier, if you remember, this is quite important. And also it is helpful to compare the physical behavior with the numerical model. So here, once you select your structure, as you see here at TLP, we can have, search and heave and pitch restricted and compliance modes, or you can carry out also in other modes of the free oscillation test. And for the experimental stuff, you have to carry out those tests at least 10 times. But in a numerical environment, in a fast environment, we can just, of course, run the simulations at once. And the second type of test, actually known as regular wave test, in order to characterize the dynamic behavior of the system and offer an insight into its underlying physics, we need regular wave tests. But in real life, actually, our structure, of course, will not survive in regular wave conditions, but these tests were designed to obtain the platform motion, response amplitude operators, in abbreviation areas, and the tandem tension transfer function if you are working with the TLP. So here you can again identify different wave and wind headings and wind conditions to see the differences. And here, just briefly, I will continue. I think time is running very fast. So here, after you carry out regular wave tests, you can investigate impact of a wind and wave heading angle on search direction or any degree of freedom. Of course, the meaningful one you should select. So here on the left-hand side, you see search response amplitude operators for 3 different wind models. So the largest response as expected with no wind case, and the smallest response is observed with a soft-end loop system. Here, soft-end loop system means actually if you are carrying out hybrid experimental setup, So if you are modeling hydrodynamic part in a lab environment and you are modeling the aerodynamic thrust using software in the loop system to generate turbulent wind conditions and relevant thrust forces, and predefined thrust in between, this indicates the constant wind value. And on the right-hand side, you see the head seas and quartering seas. So if your structure observe different wave headings, what if the response amplitude operators, if there is any change or not, you need to see this one. Of course, for a TLP, this is not an issue, and for others as well, but you have to test this one. So platform motions are relatively insensitive to wave heading, as you see. And this is again numerical and experimental comparison. Actually here, you should just check whether all of the motion and tension force responses show good agreement with wave periods between 5 to 20 to 25 seconds, considering the resonance conditions. And if you have different values apart from these values, it is not a problem. And as you see here, you may ask why we have a gap between the numerical and experimental setups. Here, it's important to mention that in numerical analysis, we have some theoretical assumptions. So all the potential flow theories and others, time domain analysis, frequency domain analysis, all the theoretical assumptions may have some numerical instabilities and differences. And on the other hand, when you are carrying out experimental stuff, again, you have to simplify your structure to build and measure the relevant quantities. So this gap actually, we understand the reason as viscous damping increases. We defined an artificial viscous damping in the numerical environment. So as the viscous damping increases, the peak responses decreases here, and which can explain the overestimated response amplitude operators due to fast simplifications at around surge and heave natural periods. So as you see here, using an open source scope is very advantageous actually, because you can solve the problem. Even though all those are based on the theoretical assumptions, you can write some scripts and solve your problem, or whether it is solved or not, you can realize. And of course, your structure, if it is a floating wind turbine, it will survive in the real sea environment. So you have to carry out a substantial amount of irregular wave tests. So you can have different wave and wind headings. You can describe turbulent and constant conditions. And you should also consider the environmental conditions. You should check the sea states and then run simulations to see the performance of your system for the deployment area. And here, I would like to show you some of the tests from irregular waves. Here, this video from a storm condition. So which means that here, significant wave height is around 8.5 meters. In the meantime, the peak period is 10.13 seconds, and all the motions are very small, apart from surge and pitch, as it is expected. And when we have a look at the probability density functions, we can see a good agreement with standard Gaussian distribution apart from heave, but we don't expect to have an agreement in heave direction, actually. And here, all wind turbines, as you know, require complex control systems. So the Nreal 5 megawatt, which we used here, it has three main control modes: torque control, blade pitch control, and turbine shot control. And as you see here from the plots, the blade thrust significantly affect the response of the system. So all drift and trim displacements follow this trend. And for the extreme condition, actually, the rotor is shut down after 25 meters per second. But there is, however, significant drag force acting on the structure. As you see here, still we have some surge. And just to remind you, there are still a lot to carry out in this field. When we have a look at the technology readiness levels, If you remember, I mentioned earlier that most of the foundation applications are monopile right now. So fixed bottom wind turbines are in the commercial application stage, but floating wind turbines is at the earlier development stage, but there are huge, numerous number of studies to make it commercial application. Recently, we have presented important progress in offshore floating wind turbine at the ISSC Congress. So I will just mention some of the things before I leave the floor. A number of full-scale floating wind turbines are currently in operation. Pilot floating wind farms have now been operating for several years. You see some of the examples from Highland, Scotland on the right-hand side. And commercial wind farms are currently being developed, high wind, and all the scarce data on wind turbine loads measured at sea are available for certain projects. And modeling techniques have progressed both numerically and in the physical testing. But there remains some uncertainties in the hydrodynamics of the floating wind turbines. And another important findings is known as high fidelity integrated numerical simulation tools were developed and are now being validated by full-scale field deployment of floating wind turbines. And hybrid formulations coupling simplified rotor aerodynamic models with CFD hydrodynamic models are continuously investigated, like software in the loop system. And aerodynamic loads predictions with good levels of accuracy and low computational burdens are of great interest for the preliminary design of floating offshore wind turbines. And CFD studies of the coupled aerodynamic and hydrodynamic response of floating offshore wind turbine are typically addressed under the assumptions of rigid bodies for the parts interacting with CFD mesh. And a good trade-off among accuracy of simulation, CPU time, demand, and out-of-the-box functionality is nowadays represented by potential flow methods. These are the, as I said, the state-of-the-art review of results over the last 3 years that I wanted to mention if any of you are interested in this field. And my last slide is about the offshore wind targets and challenges, what is required more. Still, we need to improve the design and layout of offshore wind farms. Later on, our research assistants will describe the wake effects in the wind farms and the layout optimization studies as well. And still, we need to increase the reliability, accessibility, and efficiency of offshore wind turbines. And still, we need to design special purpose vessels for installation and their access. And there is a need to optimize the maintenance, assembly, and installation of offshore wind turbines and their substructures. And serial production is quite important as well. And development of energy storage systems for grid management allow high levels of wind power in the electricity system is required as well. And development of special planning is still under importance for many countries. And also upscaling of wind turbines is another issue, which Putra will be talking about, I think, after me. Thank you very much for your attention.
Dear Elif Hocam, thank you very much for your nice presentation and very nice information. So it will be a basis for the next presentation, certainly. So how is the conditions or status in Turkey? Do we have floating offshore possibilities in the near future, or?
Actually, right now we don't have any floating or any offshore wind system, but there are some feasibility studies are running currently. So I don't know whether in near future or not, but I believe that one day we will have in Turkey as well.
Mm-hmm. Okay, thank you. If we look at the questions, I think there's one comment. Thank you for your nice presentation. Just one note. Aqua is capable of solving hydrodynamics in time domain too.
That's true. Yes, Bergüzar Hocam, thank you for your comment. That's true. Just Aqua has some meshing problems, but of course it is capable of doing all those analyses as well.
Oh, I think there's one more. Elif Hocam, çok güzel ve faydalı bir sunumdu. Çok teşekkürler. Which methods have you used for numerical model calibration and validation?
What do you mean by methods? Actually, we have used all the validated numerical tools, like using FAST and all the unreal simulations for all structures.
So the codes are already validated for many cases, right?
Yes, that's
available experiments. Okay.
Experiments are not open, actually. I mean, experimental data is always, as you know, very precious. And the companies, I mean, the example that I showed, it was the Iberdrola's concepts that we developed. So you cannot, I mean, reach some of the data. For example, I think in recall, any benefit for the use of cage type floating platforms, weight perhaps. I mean, weight issues always is like a secret for that kind of structures, but there is always some other ways to work out to find the important parameters.
Okay, thank you.
Thank you.
Is there any other questions?
Sorry for taking too much time, I think.
No, it's okay. Okay, then I guess we can continue with Putra. Hi, Putra. Hi, Putra was a Master of Science student and research assistant in Civil Engineering department. He also graduated from the Aerospace Engineering department, so he was a good candidate to collaborate between the two departments, actually. So he was able to work on both aerodynamics and hydrodynamic analysis by using OpenFast in his thesis, and recently graduated and accepted for PhD. So he will continue for PhD studies. Congratulations for that. And so thank you for the presentation. So we will be listening to you. Putra, it's your turn. Thank you.
Okay, actually, I still cannot share my screen at the moment.
Oh, okay. Just a second. We can, yeah. Can you try now?
Okay, let me try the screen.
Okay.
Okay, could you see my presentation?
Yep.
Okay, so good afternoon, audience. Thank you for spending your time attending this workshop. So my name is Muhammad Juanda Putra. This is my first conference actually, so I'll be teaching this type of thing for the first time. I'll be talking about offshore wind turbine aerodynamic and hydrodynamic analysis with OpenFast. So I will actually introduce OpenFast and everything and how to install that, and we will try to do one simulation case for today. So I will start my introduction with explaining what is OpenFast, what is the modules inside that, the validation case for OpenFast, how to install that, what is the input and output files and everything. I will just make the presentation fast so that we can go to the trial quickly. So OpenFast is a non-linear code used to simulate wind turbine. So it's for simulation purpose. This is open source code, so everyone can contribute to developing OpenFast. So it's developed by NREL, National Renewable Energy Laboratory in US, and used to be called FAST program actually. So until 2016, as Nilai Hoja said earlier. So after that, it's called OpenFast, and it's based on Fortran languages. So we need Intel Fortran compiler for this. We can use OpenFast for 2 or 3 bladed turbine, upwind or downwind. So this is upwind actually. So the rotor is in the upstream with respect to the wind directions, and downwind is the other ways. So okay, so this is the modules we use actually to model floating offshore wind turbines. Actually, it's very complicated because the structure is highly moving and everything. So there are several modules we need actually. For external wind load, we use inflow wind. So for the wave condition, we can directly input to Hydrodyne. And for aerodynamic calculation, we use Aerodyne. There are two versions actually, 14 and 15. The latest one is Aerodyne 15. And hydrodynamic loads to again Hydrodyne. We use Serpodyne to model the actuator and controls. I'm not actually very familiar with Serpodyne either, but we are interested in the power and torque from the control. So Elastodyne is used for the structural dynamics, and because we are using floating offshore wind turbines in this EuroCC seminar actually workshop, so we will also need to model these mooring lines, and for that we have several modules in here, and today I'll be using MAP++ module for mooring dynamics. Okay, so OpenFast is well validated actually with the real turbine in here with Siemens 2.3 megawatt, as we can see. So it is able to predict actually the power curve of the turbine with several limitations of the studies explained in the reference. I will show my reference later. It has also been validated with lab experiment like in marine in here. So this is for OC4 semi-submersible. And as we can see, they tried via mooring, MAP++, Moordyne, and they compare it to marine's experiment. And the motions actually are pretty much agree in heave, search, and everything. So we can access the reference later. It has also been compared to another codes like in OC4. So this is actually comparison of so many codes, aeroelastic and hydrodynamic codes actually, and the results is pretty much agree with one another. So I will explain how to install OpenFast actually. I need to emphasize at the beginning that there is no need for compiling OpenFast. We can just download it from the GitHub platform. However, it has several dependencies, and if we successfully compile this in our computer, we are sure that we can run OpenFast without problems. And the dependency is Fortran compiler, actually Intel Fortran compiler for most of the operating system, but for Mac and Linux, we can use GNU Fortran compiler. We also need mathematics library, BLAS and LAPACK for Mac and Linux, and mathkernel library for Intel. So let me emphasize this. This is Intel compilers. So in case of our computer running in AMD processor, for example, then don't try this at home. We can just go with the Linux way in that case. So to build OpenFast, we need C++ CMake and GNU Mac for Mac and Linux, and Visual Studio for Windows. Let me show the documentations from OpenFast. This is actually main documentation. So if we Google OpenFast documentation, it will give us directly this link. And yeah, it contains everything, installing documentations and everything, that how to run the test and everything. So for the building, actually for Linux and Mac, we can use Anaconda for that. And it's pretty simple, actually, just 2 lines. I'm sure that all of Linux users are familiar with Anaconda. Just create the environment and then directly install. So just 2 lines actually for installing. And for Windows, it is actually longer, but I've been through that because I'm a Windows user, so I will explain it straightforward actually, directly how to do it. So we need 3 steps actually for building the dependencies. So first one is Visual Studio with C++ CMake. We need to do it in order actually. So Visual Studio first, then Intel Fortran compiler, then MKL library. So we can obtain Visual Studios actually from the website. We can download from here, actually any version will be good, but for me I use the community editions. It is free actually, and it's enough to build OpenFast. Okay, so we download it, run it, and this is the interface of the program, actually the first pages for the installations. I use this desktop development with C++. However, we only need actually this C++ CMake tools and 1 SDK files. So if we don't want to install all of this, we can go with the individual components in here. And we can just search for C++ CMake tools. And then if we scroll down, we will find this Windows 10 SDK. Or if we are using Windows 11, we can also use the most updated versions. And then after that, just directly click install. and then it will ask to reboot our computer, then just accept that. So after that, we need to install Intel Fortran compiler, and this is the keyword actually for YouTube for Google Intel Fortran compiler, and we can download this standalone versions in here. For me, I like to use online installer better because I know it's already working, and it's light, actually only 13 megabytes. So I download that and then run it. So this is the first interface of the program. Just accept the terms and conditions because we only need to install one program here. We just directly continue. And then this is important so that if we install Visual Studio before Intel Fortran compiler, they will directly actually understand that we have Visual Studio inside and integrate it to Intel Fortran compilers. So just click the consent and click the install. After this, we can click actually finish and close the installations. And after that, we need Math kernel library. So we can obtain it from here, Intel 1 API-based toolkit. Actually, this is the keyword for Google. Just download this toolkit, actually, this one. Input our operating system. Again, for me, online installer is better. Again, only 13 megabytes. Download it. And then run it. This is the first installations interface, actually. As we can see, a lot of programs actually in here, but we don't need all of this. We only need math kernel and then one thread building blocks, actually, because we want to make open fast from the beginning. We want to build it. So just click customize and then, sorry. So I was click this customize, not continue. And then just tick these two things, actually, math kernel and then the thread building blocks. And after that, again, integrate it with Visual Studio, install, and yeah, at this moment, we have all the dependencies for us, actually, for Windows users. Now we can go with building OpenFast directly from GitHub, actually. Let me show in here. So this is the website. Just type GitHub OpenFast. It will give us this link directly. So many users has accessed this, and so it's in the first, actually, in the order. So this is the library for the OpenFast. We have two options here. For those who are familiar with Git, you can just clone this directory, or we can download it as a zip file and extract it. What I want to show in here is actually they have this section here for the release. So the latest version is 3.2.1, and there are other release in here. Actually, they also tabulated what has been developed, so what has been added, what has been removed from the OpenFast. And as we can see, actually, let me emphasize once again, so we don't have to build it from scratch. We can just download these files in here, actually, if we want to run OpenFast. This is OpenFast, the latest one. However, for me, I like to build it. And when I was doing my thesis, I was still in version 2.5, actually. We can go down and download that, actually, from the assets in here. We can download the zip files and then extract it. Okay, once we extract the files, we will get this actually the same as in the website. We need to go to Visual Studio Build and then fast building solutions. So after clicking that, they ask us to upgrade to the latest version in here because we are using actually most updated version of Visual Studios. So just click OK for that, and then we need to pick release from here. It dependent on us. If we want double precisions, we can use release double. For me, a single precision is enough. And my program is, computer is running on 64-bit computer, so I'm selecting X64 in here. After that, just click build and build solutions. And then the Visual Studio will actually compile OpenFast for us. As we can see, we have succeeded building the OpenFast. After this, actually, Visual Studio will create this folder called build. Inside of build, again, binary, and inside binary, now we will have the same thing as what has been shown in the website. So let me emphasize, we don't have to build, but if we build it from the scratch, we know that it will work on our computer because all the dependencies are already there and integrated. Okay. Sorry, where am I? Okay, so today actually we will run one trial, but before that, let me explain what is the input and output for OpenFast. So again, this is the same documentations for OpenFast. I want to take your attention to here. Actually, this is the outlist parameter. All the outlist, all the parameters we can extract from OpenFast. Let me show the files. Actually, I've downloaded that. There are approximately almost 1,000 parameters we can extract from OpenFast. As we can see for aerodynamics, we have power coefficient, torque coefficient, thrust coefficient, etc. We have the power, the tip speed ratio, and everything. For elastodynamics, it is even more. We have deflection, forces, moment, and everything. We have all data for the tower, rotor, generator, everything, including the platform. We can check for the platform motion, surge motion, heave motion, and etc. Okay, for example, in here, so there is this platform sway, platform heave, and it will give us displacement in meters, and for the pitch, for example, in degrees. Inflow wind is for the wind velocity. Servodyne, I'm interested in these two actually, torque and power. And from hydrodyne, we can take the wave elevation, which is important for calculation of PSD and RAW, which we can actually see later. Okay, so in OpenFast, there are so many, actually several different output type. Actually, we don't have to select. We can do everything all at once. So summary is for telling us what we have been done in one simulation. So for example, we are doing 25 simulations. The summary will tell us what is the difference between one simulations and the others. Out is for the time matching tabular output. So this is normally the one I use actually. So we have all the parameters I explained earlier inside this .out files. For those who like to use binary type, out binary is also available. Echo is for checking whether what we input is the same thing as what the program reads actually. So this is important if you are running OpenFast for the first time, whether to check the input is correct or not. We have checkpoint, and also this one is actually new release in OpenFast if I'm not mistaken, or maybe in the latest Fastpoint 8.16. So we have the capability to visualize the turbines. This is the one I did in here for the OC4 semi-submersible, and I will teach actually how to do this one today. So we are using NREL 5 wind turbine atop OC4 deep sea wind semi-submersible, and we can find that from the same directory of GitHub OpenFast. So there are several cases actually here, regression test for us to check actually dependent on what we need. For today's presentations, we will use this one actually, OC4 semi-submersible. And then for the turbine, we will use NREL 5 megawatt turbines. Okay, so it's in this one, the 5 megawatt baseline. Sorry for that. So I have downloaded most of the files here and put it in one file for today's presentations. So this is the binary we have compiled in previously. I put it in the same file as the other inputs. Actually, it's easier for me. This is my habit to do it this way. And let me first run it. Then I will explain the input files. So we need CMD to run OpenFast. We can type CMD and then copy this directory. So we can change directory to our directory now, and we can check whether it's true by checking the content of the directory. Or it's easier actually just to click in here, CMD directly, and it will directly start in this directory for us. So to run OpenFast, we need FST files. This is the main input, actually the main files for OpenFast. Just type right now OpenFast 64 because I'm using 64 bits. And then the input name. So run one in this case, and then .fst. Okay, so this is the interface when OpenFast is running. Actually, we can use .exe in here, but actually it doesn't matter. CMD already understand that this is an applications. So I will explain the input right now. The output is fun actually, but the input is long. As Nileho just said, most of the time in research is actually in the pre-processing, and yeah, there are so many input files we need actually. And this is the main one to couple all of the modules inside OpenFast. This is the simulation control. Actually, I suggest to use the echo actually for the first time. And this is the maximum simulation time. I'm using only 15 seconds in this tutorial. We can run up to 9,999 if I'm not mistaken. I'm using 0.01 for the time step and everything. So this is the features and switch actually. This one is for the structural dynamics. I'm using one. One is Elastodyne, as we can see in here. For inflow, we use one in inflow wind. Aerodynamic, I'm using the latest version, Aerodyne version 15, and Servo, I'm using Servodyne. Actually, this 4 is enough to do onshore wind turbine. However, for offshore, we need at least 2 more modules. This one is Hydrodyne for hydrodynamic loads, and then for floating offshore wind turbine, we need catenary mooring lines and actually tendon in TLP. So mooring dynamics, I'm using MA++ in these simulations. Okay, input files for each modules, Elastodyne in here. Okay, so this is Elastodyne. I just input the name, inflow wind, Aerodyne, everything is from this folder to here. Servodyne and etc. We can set our output actually in whichever format we want. Also the status time, this is the screen time for us actually to check what kind of output we have. So OpenFast also capable to give us animations actually for visualization purpose, but it's not necessary. We can just select 0 if we don't want that, because it will increase the file size. Let me explain actually now the module input. Let's start first from Elastodyne because this is the first module. Okay. Maybe it's good if we also compare it with the definitions. So this is the definitions of NREL 5 megawatt. From NREL, this is publicly available. And as we can see in here, degrees of freedoms, up to second side-to-side tower is for onshore. As Elifo just said, in offshore floating platform, we add actually another degree of freedom, which is this 6 degrees of freedom actually. So this is initial condition specified by NREL. This is the turbine configurations, which actually are from this table. So we have 3-bladed. The rotor diameter is 126 meters in here. So the tip radius will be half of that. And this is for the hub actually. Hub is 3 meters. So the radius of the hub will be 1.5 meters. We can see the precon everything minus means it's upwind turbine. As we can see in here, this is 2.5 degrees and we input minus 2.5 because it's upwind. Overhang is 5 meters, again minus because this is upwind. Shaft tilt also minus 5 degrees as we can see in here because it's upwind. Okay, so all of these definitions inside Elastodyne can be found in this PDF actually developed by NREL. However, I want to emphasize this. This is the definitions for the blade. Actually, let me show it in here, which is this file. Okay, so in here, what is important, we have the blade mass, stiffness in edgewise direction, flapwise direction, and everything, which is actually the summary of this table, actually, very big table. But in OpenFast, we only input up to edgewise stiffness in here. So it is the same, actually. And if we plot it, maybe I have done for that. Okay, so this is the non-dimensional span-wise distribution. As we can see, mass is shown by the black line and the stiffness is shown by the red line. So it is from these definitions. The same for the tower. Actually, we also input the same mass and stiffness, everything. And this is for the output, as I showed earlier. We can put as much as we want actually from the outlist parameter, but this is actually what I'm using in my thesis. I am interested in this much things, but actually I didn't use all of it because yeah, there are so many outputs actually we can do. Okay, moving on. Next one is inflow wind. So this is simple actually, just for the wind. So in this trial, I'm using this actually steady wind. So 90 is the reference for the hub height. Actually, we don't have to put 90 in here. If we know velocity at any elevations, we can use that and put the power law exponent, and we can get the velocity at the reference, which is in this hub height. However, if we want to simulate another case, we have to do it in TurbSim actually, and input that in these files, and then change this either to 2 or 3, or depending on what we need. And now I believe it's aerodynamic. Yeah. So in aerodynamic, we specify the environmental conditions. This is for the fluid actually. So air density, kinematic viscosity, and everything. And what is important here is this one, aerodynamic. So airfoil, actually airfoil data. So in previous workshop, actually SG already explained the 2D airfoil polar data and everything. It's also the same. So that's the input for our aerodyne. As we can see here, we need coordinate. Coordinate is for the X and Y coordinates of the airfoil. Maybe I can plot that. Yeah, so this is the plot of the coordinate. So we start from here at 1 and then moving in counterclockwise directions. We also need the polar data, as can be shown in here, CL, CD, and CM. So it is lift, drag, and moment coefficients, the same plot that SG shown. So we need this kind of data, and we can use actually SU2 for that, R foil, X foil, depending on which one actually we are familiar with. But we have to take into account the what SG has said in her workshop. So after that, where is my arrow then? I'm sorry. Okay, we are inputting the blade aerodynamic input in here. So it's actually this one, consisting of the twist, actually core and everything, blade, airfoil definitions and everything, which is coming from this table. Actually, so for example, blade ID1 is cylinder, and it goes on until NACA 18%. So we number this one actually 1, 2, 3, 4, 5, 6, 7, 8, and it's used in here 1 until 8 for that. So it is actually like this. This is pictures from Zanon et al. So this is how we model the blade in blade element momentum theory. For the tower, actually, we are not inputting as separate files because it's a simple cylinder. So we just need the tower diameter and then the drag, because a cylinder do not produce any lift actually. So for the output, we can specify whichever output we need. And again, let's continue to the servodyne. In servodyne, for me, I didn't touch this file that much. Actually, I just specify the outputs that I need, because this servo is actually for control purposes. Now, moving on to the hydrodynamic part. This is hydrodyne. We have to specify the fluid density, water depth. So this is basically environmental conditions. This is the wave conditions actually. What is the significant wave height? What is the peak period and everything? And we need potential flow model from WAMIT, as Elifo just said. But actually, we don't need to use WAMIT. We can use HAMS, NEMO, and others, as Elifo just already explained. We need the volume of the platform and everything. But this one, is displacement. Okay, so this one is the volume actually for the submerged body. And moving on, this is the vertex definition. So this is for the members. As we can see, we have the coordinates actually. So this is the vertex. For example, vertex 1, this is the X location, Y location, and Z locations, and in real dimensions in meters. So this is the property set. What is the diameter and what is the thickness of the members? And this is how we actually connecting one vertex to another. So we have approximately 22 members in here connecting 25 members here connecting several joints. This is for the drag coefficients of each members. Okay, and moving on, this is for the ballast actually. So three columns actually is ballasted actually. So we have 3 in here. And then water ballast is used in member 2, 3, and 4, also in member 5, 6, and 7. Okay, so for aerodynamics, I actually like to output wave elevations because we want to calculate RAO, and it's important that we have RAO in calculating the. It's important that we have wave in calculating the RAO. So for the mooring lines, actually I'm using MAP++. We have the mooring lines diameter, density, and everything. This is actually from these definitions in here. For example, mooring line 1, this is the locations actually for the anchor. This is the X coordinate of the anchor, Y coordinate, and Z coordinate is in the seabed. So this is minus 200 meters. And for the vessels in here actually, so this is for the fairing leads actually. So 24 meter, 35 meter, and etc. We have to do this repeated twice actually for 240 and 120 degrees because we have 3 mooring lines. And after that, yeah, so after running the open fast, let me check it. Did I put pause? Okay, so it's finished. Okay, so I actually paused it. Okay, now it's good. So we can check actually real-time data for this because I paused it earlier. So now we have real-time in here. So this is the power versus time. So as we can see, as the simulations get better, so at initialization state, we have actually poor result, then it gets better. So this is NREL 5 megawatt, and we're expecting 5 megawatt output actually from the simulations. As we can see, it reaches to 5 as the simulations get steadier and steadier. We can check actually for the heave motions and everything, also for the turbines, as well as for the flap edge and edgewise bending moment. So we have real data actually. I suggest to use GNU plot for that. GNU plot is very powerful for plotting actually tabular data. We have option to actually bring it to Excel and then plot it from Excel, but it will take so much time actually for that, and there are actually big chance for human error in that. Okay, since I use actually 2 in the FST file, so it will give us visual actually VTK files. So this will be the animation files, actually visual toolkit files. And we can use ParaView for simulating this, as we can see. Okay, let me check whether I have computational power to do this. Okay, so we'll just close this. Okay, so ParaView is not opening at the moment. I'm waiting. Okay, we can just input the VTK files like this, all of it, and then apply. And from that, we already get the 3D actually turbines in here, as we can see. We can do a lot of things in here. We can put, for example, colors. Let me just show one. For example, for this one, for the horizontal surface. So it is normally in yellow. Yeah, we can be creative in this part. And let me show what I've done actually. So in my research, I was studying about how to upscale wind turbine. And this is the flow chart of my study. And actually, this is the baseline turbine. I'm using linear scaling. Actually, I actually use OpenFast together with hard-op co-blade hams actually for modeling the platform geometry. And I'm using MAP++ to calculate the mooring line stiffness and everything. External hydrostatic restoring matrix. So I'm upscaling NREL 5, for example, to 20 megawatt, but I just show until 15 in this presentations. And this is the performance actually. So this is comparing 5 to 20 megawatt turbine side by side, as we can see in here. The rotational speed decreasing while the turbine size getting larger. We can compare actually the surge motion, the pitch motion, and this is for the power and thrust. We can do pretty much for everything depending on what we need. And this is some of the result. Actually, I will just highlight it. So we also optimize turbine in my studies, and the result is as follows. This is power curve, typical power curve actually for NREL 5 megawatt, actually for all turbines. And we have seen a slight actually improvement in the power because of optimizations. This is surge PSD. For example, natural frequency in surge motion is located in here. This is actually natural frequency for pitch, but it also shows in surge PSD, which means that surge and pitch are coupled and everything. We can see the response amplitude operator of the platform and etc. Response amplitude operator more than one means it is actually moving more than the wave. So it's actually resonating with the wave actually. So as Elifo just said, that we are trying to actually go out from this. However, still in the original NREL 5 megawatt, as we can see, the natural frequency lies inside the wave excitation regions. Okay, so this is my reference for today's presentations. Actually, I'm not going to take much. Thank you for listening. Actually, if you have any questions, I'll be happy to answer. Thank you.
Great, thank you, Putra. It was a very nice presentation. Nice explanation of your applications. Lots of input files, as you can see. It is very easy to run them on Linux systems as well. So as you said, it will be easy to compile and run as you just preparing the correct input files and what you want to get at the end, and visualization of the results and solutions are important parts, I guess. So thank you if I summarize like that. Let's look at the questions. Which international standard do you prefer during simulation for structural tower of wind turbine on offshore simulation? For instance, fatigue resistance of tower should be in accordance with the international standard that's called structural steel fatigue resistance. What about wave situation? Is there any standard during finite element module implementation about the wave impact from sea on tower? If so, what is the standard code? Okay, for civil engineering perspectives, I guess I'm sure there are, for wind energy applications, there are standards, I know.
Yes. So actually, I believe, yes, there are standards for wind energy. IEC standard, actually, it is the well actually used code in wind turbine. So actually, wind turbine is rated IEC 1, 2, and 3. Actually, I'm not so familiar with that either. I believe that this question is gonna be better answered by Elifoja, but okay.
Let me answer. Thank you, Putra. The thing is, there are some main design criteria in industrial standards. We have IEA, IEC for the mooring redundancy, operational, and in order to increase the safety factor, actually. And also it covers the stability, damage stability, and type of criteria we can define whether it is static or dynamic response based. And also we have ABS, BV, and DMV, LR load registers, and class NKs. Also all are the classification societies. All are providing so far for the offshore industry in terms of mooring redundancy, stability, damage stability, and depending on the type of the criteria. And also for design format and the materials. Sometimes they just identify steel and concrete and so on. But all the classification societies are also working very hard to develop more standards in this new industry. But mainly at the moment, they are considering the design aspects and the stability and safety issues. Fatigue loss, of course, it is quite important for long term, especially, and for the structural resonance also we need to consider. But all those standards are still in development as well. But thanks for raising this question. It is quite important.
Yes, this is very important question actually, and yeah, you are asking to the right people to answer.
I guess for the wind turbines, IEC standards are the common ones, right?
Yes, so it
for
was
the design, for the operation, but you need additional standards for the platforms and everything, of course, most probably. So as Elifo just said, but to apply those standards, you need to do simulations for extreme cases, right? I mean,
exactly.
Yeah.
50-year extreme conditions and to test under all load cases, actually. Yes.
To find the envelopes and see if the system works in a given desired envelope.
True.
Yeah. Okay, great. Thank you. Can we define a gurney flap type airfoil at OpenFast? That's a nice question.
Actually, I'm not familiar. What is gurney flap type airfoil, Nilai?
You know, if for the airfoil at the trailing edge, if you have this flat surface down, yeah, so additional airfoil character. I guess you need a airfoil database for that. If you have a gurney flap,
we can just model it actually, and then do the polar data for that. And I'm sure OpenFast is capable for doing every kind of simulations if we provided the right input. So we can do most of things actually in OpenFast. Even they tried for new versions for kite. Actually, there is one OpenFast kite, so it's already there. For wind farm, actually there is fast farm. But mine still stuck at version 2.5, so I will just update it.
New versions have the farm, fast farm, and also for the kite modeling, kite type wind turbines are getting popular as well to control them, and they have different airfoil sections as well. So as long as you can provide the airfoil polars, you can simulate. Yeah.
Yes, exactly.
Okay. How did you couple ROSCO controller and OpenFast?
Okay.
That's another question.
Yeah, this question must be coming from expert, actually the one who is in the community. So we need to apply ROSCO in Servodyne, actually in here, libdiscon. This is actually output. So this is actually the dynamic link library of ROSCO. It has also discon input and everything. And inside this discon input, we have actually the tuning for the, actually, this is the kind of tuning we have. So what is this expected CP with different TSR and everything. So we can tune the turbine actually in ROSCO. However, I'm not control guy, but I'm sure it's doable. And that's it. Actually, only these 3 lines. is needed if you want to implement Roscoe to OpenFast.
So maybe the input file is critical to prepare.
Yes, always input file. So
Again.
output is fine, input is critical.
Yes. Okay, thank you. Is there any other questions we can try to answer, or any comments?
Yeah, I will also provide these test cases later.
Yeah.
Hopefully everyone can access this.
Yeah, we will update these test cases to Indico webpage probably, so you can get them from there. Okay, so thank you, Putra. Thank you,
Thank you so much for
Elifojam.
listening.
So we will have 10 minutes break, a coffee break. We can get our teas and then we can meet again at 15:15 for the next presentations. See you.
See you.
Merhaba, merhaba Ata.
Merhaba hocam.
Evet, nasıl gidiyoruz? Herkes iyidir umarım. Yoğun bir workshop, güzel çalışmalar dinliyoruz. Okay, hi everyone. So we will continue with the nice presentations. Last two presentations will be about wind farms and wind turbine wakes. And first presentation will be given by Ata again. So we have already listened nice presentations, so it's going very nicely so far. I hope you are able to following. So Ata, can you share your presentation? I guess we can start slowly. So maybe still people coming back.
Okay. So if you can see it, I think I may start.
Yeah. Yes, you can start now. Thank you.
Hello everyone, it's Ata again. Now in this afternoon session, I'll talk about introduction to wake models and wind farm analysis. I'll talk about wind farm aerodynamics, wake models and wind farm analysis. So in this section, there will be no applications, but I'll try to give an introduction to these topics. And as I believe in the next presentation, there will be more detailed information about the wind farm analysis and some applications. But before that, let's build a background. So in the wind farm aerodynamics, I'll talk about the wakes and the wind farm interactions. So we have talked about wake a lot. So it is a reduced velocity behind the turbine, but how does it occur? So as we know, wind turbines extract energy from the air, so it's their purpose. So they have to generate power. So that's why they physically take energy from the air, which reduces the kinetic energy of the air. It's like the opposite of an aircraft propeller. So in a propeller, the aircraft engine gives the power, it accelerates the flow, and from Newton's third principle, the aircraft will get a forward thrust force. So this is the opposite one. This time, it is the air that gives power, and then the wind energy generates energy. So that's why we have reduced kinetic energy downstream of the turbines over here. And also, this is rotor-induced vortices to flow, as you can see over here, because of the rotational motion, which increases the turbulence, and also it enhances mixing. In other words, the turbulent diffusion, as we can see over here. So at the end, we have a low velocity, high turbulent flow downstream of the turbine. So when we see the velocity profiles near the turbine, which is usually distances close to 3 diameters of the turbine, we see some asymmetrical velocity profile, which is due to interactions with non-rotating elements like the tower and the ground, and also sometimes the effect of atmospheric boundary layer is seen. Also, we can see that there's greater maximum and mean velocity deficit. So it means that if we put a wind turbine close to another one, then we will get a less power generation due to this less velocity, because as you know, the power is proportional to the cube of the velocity. Also, we know that the effects of flow interactions with turbine components are present, which is seen from the unsymmetrical velocity profile. But when we get away from the turbine, we see a greater wake diameter due to the mixing over here. So the sketch also shows the expansion of the wake. So in these figures, we see that the wake diameter is like around 1.5 diameter of the turbine, close to turbine, but as we go away, so it becomes larger. Moreover, the unsymmetrical shape disappears. Instead, we get a symmetrical Gaussian velocity profile away from the turbine. And we see less maximum velocity deficit and mean velocity deficit than near the turbine. So it will be wise to put a turbine away from an upstream one to get more energy. But so this is actually the tricky part of wind farm. So you have limited areas, so you have to get the best maximum power as possible. So which would be more beneficial at the end. So this is actually a big question. Because still in the wake, we see mean velocity lower than the free stream. So let's say that we put a turbine. So this is a turbine. So we have one diameter distance like here. So we still have velocity lower than free stream value, as you can see. And also we have still greater turbulence level than the free stream compared to the clean coming flow. So although the main element is the wake effects, there are still additional effects in a wind farm. For example, we have local blockage effects, which is a positive thing actually. So we have this actuator disc aligned on this straight line. So we have this wake behind them and reducers. But as you can see, in between we have some increased flow. So from this color one, we see that it's greater than 1. So these are called local blockage effects. So in a wind farm, we can see some local accelerated flow. Also, we have the farm blockage effect, which is the farm scale flow induction, and I'll show you in the next slide. So this is then a sketch from the famous article of Porte-Agel et al. So this is different flow regions within a wind farm, and also we have the atmospheric boundary layer. So just before the upstream of the wind farm, we have the induction region. So in here, the blockage effect from the wind farm produces a deceleration of the incoming boundary layer flow. So it is visible over here as well. We have a reduced velocity just upstream of the wind farm. So, and also it increases the height of the atmospheric boundary layer as well. In the second region is the entrance and development region. And here we see the formation of an internal boundary layer and the turbine wake flows. So we have a heterogeneous flow over here due to the wake and all these interactions. Then this both atmospheric boundary layer and internal boundary layer adjusts to the wind farm. But this region, the length of this region depends on the size of the wind farm. So if we have a very large wind farm, okay, we'll have a long fluid developed region, but otherwise it will be shorter. And also at the end of the wind farm, obviously we have the exit region because of this end of the wind farm, end of the wakes. We have a large accelerating exit region, and at the end, we have the wind farm wake. So the wake caused by the wind farm itself. And after a sufficient distance, again, this and reduced velocity disappears as well, but it may require a lot of distances. So at the end, in reality, it comes to the wind farm array efficiency. So how efficient your wind farm is in terms of power generation, and it depends on many variables. First of all, there's wind characteristic, which is a very important thing. So the velocity, its fluctuations, its directions, about temperatures, it all have major impact on the wind farm performance. And also, of course, the turbine rotor design has a tremendous effect due to its impact on the on these wakes, as you can see here, this famous photograph. Also, we have rotor flow, non-rotor components interactions, and which also impacts this, wind turbine wakes. Wind farm control is an important point, which is actually wake mitigation. So, for example, we have this upstream turbine over here. It directly, its wake directly passes the downstream turbine. But what if we put some yaw angle, and with that we can change the direction of the wake so that the downstream turbine will see a cleaner flow, which may result in a higher net energy. Also, for example, some floating offshore turbines, there are works on turbine repositioning, for example. What if we move the turbine itself? So this is an important topic as well. Wind farm layout, obviously, it is very important. What if we did not, put these turbines in a straight line, but we put some turbines in between? But it depends on the overall wind characteristic of the region, also the terrain if it's an onshore wind farm. And this is the other points of terrain and surface conditions as well. And also the wind farm size is important, as I mentioned earlier. So it affects the development of the internal boundary layer and all these regions within a wind farm. Now we can continue with the wake model. So first I will give you a glance of the theory. So how, in general, how the wind wake models are derived, what are their advantages, disadvantages, and also I want to show you a brief derivation of a non-wake model. Then I'll talk about wake superposition methods, which is important for the wind farm analysis. So we know wind farms contain many wind turbines. For example, in here we have like more than a dozen wind turbines. So you can simulate them through meshing. So you simulate each turbine, and around it you generate a large volume mesh, but it requires fine resolution. So because we have large turbulence scales, complex interactions, sometimes reverse flow. So with a very fine mesh, we also need high fidelity models, which in combination comes with a very high computational cost. Of course, you can simulate it. You put in a cluster, let it run for a few days, maybe for a few weeks, then you'll get the results. It's okay. You get a very nice solution of the wind farm. You can detect these complex turbulence structures, but for an application of wind farm control or area optimization works, you have to run those simulations not just once but multiple times. So it may not be feasible to mesh the whole large wind farm and get the results and do some optimization works or whatsoever. So as an alternative, this high fidelity works, we have a computational chip approach, which is engineering wake models. For example, on the right hand side we have both an LES and an engineering wake model results of an offshore wind farm. So again, we have this LES, we have very nice pictures results, and we have this wake model. As of course, you can see that it is not as complex as this one. It may not prove, its resolution is lower. It may not prove, it may not give the results you may expect in a wake, but at the end you can see the correlation between them. We can get the overall wind speeds, the wake shapes in a low resolution way. So we can use these results in other applications. So in general, the velocity profile at the downstream of a turbine is complete with analytical equations and empirical relations in these wake models. And also we apply semi-analytical superposition models to get a wind farm, an overall wind farm flow. So in a recent work, on the right-hand side, you can see the result from a recent work. So the several wake models are applied to 2 experimental and 1 LES cases. So at the end, we get an error, an average velocity deviation of around 8%, 10%. So it may be a bit much, but when you consider a work which requires a lot of simulations, then it may be feasible. So most wake models are derived by applying the conservation equations within a control volume with assumptions. So usually some terms in the momentum equations are neglected, like the pressure term, gravity term, viscous term, etc. And also, apart from that, empirical relations are introduced. For example, the wake expansion coefficient, wake radius. And usually these relations are extracted from experimental measurements or high fidelity CFD results. So they do several experiments, they get their data sets, they did a curve fit, and then at the end they can get a more or less valid relation for these variables. Most of the turbine attributes and atmospheric conditions are taken into account. This is important because in a wind farm analysis, you have to see the variation of turbine performance between wind velocity and sometimes with turbulence. So that's why it is important to take these variables into account. We see that the earlier wake models propose a top head velocity profile. For example, on the right-hand side, we can see 2 such profiles, Franzen and Janssen model. You see from the green lines, we have a constant velocity within a wake, and outside the wake, we have the reference velocity. So these models are, as you can see, computationally cheap, And in terms of mean velocity, they can give actually relatively good results, but they do not show the real shape of wake velocity profile. So that's why the modern ones propose a Gaussian velocity profile, as you can see over here. So we have a maximum velocity at the middle, and it increases as we go outside of the wake. So let's do a little derivation. So we have Bastanca and Portal-Gall wake model. So this model was introduced in 2014, and since then it's widely used in the wind energy community. So we have this control volume, we have the turbine, and due to the turbine, we have a reduced flow in the wake. So let's start our control volume over here, and it goes up to some point, up to some x distance. So let's apply mass and momentum conservation equations for this control volume, and let's neglect the viscous and pressure terms. So at the end, we have this integral equation. On the right-hand side, we will have thrust, which is equal to 1/2 CT rho A0 U infinity square. We have the UV terms, which is the wake velocity at the end of the control volume. So let's assume a Gaussian shape for the velocities, like the shape over here. So like this one. So the velocity deficit normalized by the upstream velocity is equal to 1 minus UV over U infinity. So over here, so which is equal to C of x, which is the maximum normalized velocity deficit, times exponential of some term. So R is the radius from the wake center. And we'll talk about sigma in the next slide. So when we integrate this integral equation, substitute with this relation, we get a quadratic equation of C of x. So solving the equation for C of x gives us this relation. So C of x, depending on the CT, the thrust coefficient of the wind turbine, sigma, and the D0. D0 is the turbine rotor diameter. And let's assume a linear expansion for the wake region, like this one. So as you can see, the wake expands like linearly in the control volume, which is widely used assumption in wake models. So we have the K star x of B0 plus epsilon. As you can see, it is linearly increasing with x distance. So K star is the wake growth rate, and the epsilon is the normalized initial wake half width. So this actually this distance, the initial half at x is equal to 0, what the width of the wake. So in here case, in this work, actually, Bastanca and Portal-Gall did not put a relation for K star, but in another work, this term was related with the ambient turbulence intensity. So the turbulence, in the model, the turbulence intensity affects the wake expansion, and the epsilon depends on the thrust coefficient of the turbine. So this function, I didn't put it in here, but you can check the reference paper. So this function is derived from the another wake model, and the coefficients are fitted from a LES dataset. Thus, at the end, when we substitute these terms into the equation, we get a velocity deficit as such. So we have the delta U depending on x, y, z. So we have this relation, which is C of x, as you can see. So remember, we have this velocity deficit C of x, exponential of some term. So this is C of x, the exponential, and the exponent here. So we have also the z and y locations. We also include the hub height of the turbine. We have D0, and this is our actually equation, a very simple equation to get the velocity deficit behind the turbine. Okay, so let's move on with the wake superposition models. Wake velocity distribution for the multiple turbines is determined by 2 steps. First, we calculate the individual turbine wakes separately, as if they are isolated. Then, for each discretized point, we combine these wakes, passing that point with a superposition method. So these are the commonly utilized superposition methods. We have linear sum and root sum square method with global and local approaches. So in here, UIV is the local average velocity within the rotor swept area incoming to the turbine eye. Like, let's go back. So like here, so the upstream turbine see U infinity, that's okay. But what if the downstream turbine, so over here, this turbine does not see the U infinity, it sees the lower velocity. So we have to take into account So that's why this local methods utilize this term over here. Apart from velocity, also the turbulence level of the turbulence level within the wind farm changes due to the wake of wind turbines. So some models calculated. So at a downstream location, they calculate how the turbulence intensity changes, but some do not. So if we have a model with such a capability, we can also include this term to calculate the wind turbine wake for the downstream turbines. But there's a big problem. So the wake superposition models lack a theoretical basis. Of course, they work, but there's this problem. So while these linear models preserve mass continuity, the root sum square terms preserve momentum continuity. Energy conservation as their goal. So actually the models are empirically derived, not a theoretical one. So that is why it is actually a hot topic in the wind energy community. There are additional models derived with analytical, numerical, empirical, or machine learning basis. So I did not put a list, but if you want to, you can check this recent 2022 paper to see a list of new wake superposition models. So at the end, we have the wind farm analysis. So I'll just briefly explain each method here. So we can see there are actually, we can list 6 different models for wind farm analysis. And from top to bottom, we have greater accuracy with more computationally expensive methods. So first of all, we have the wake models. You see that we have just a simple equation. So at first, we need a stress coefficient and U infinity data of wind turbines, and from there we can get the wake velocity profile. After that, we get the power coefficient of each turbine, and then get the overall power generation. So it is the simplest and the cheapest approach. Nonetheless, we cannot predict the complex wake structures and the local blockage effects I talked earlier with these wake models. They are useful for optimization, wind farm layout, and wind farm control applications, but not for research on the turbulence within a wind farm. The second one is the blade element momentum theory. It combines the actuator theory with two-dimensional blade elements on the turbine. We can include the effects of tip losses and the wake rotations in such a model. It requires airfoil performance data to combine the actuator theory with the blade geometry, but it could be difficult to get a two-dimensional data set with rotational and three-dimensional effects. So that's a big problem for this method. Third one is Lagrangian-based model. So we have the vortex lattice and vortex particle methods. So in such a model, the wake is described with vorticity sheets or particles, and the blades is represented with lifting lines or surfaces. So on the right-hand side, you can see a sketch of a vortex lattice method. So we have the blades, they are lifting lines or surfaces, and also at each rotation, the blades shed a wake vortex filaments or particles. And also it has implicit and incompressible flow assumptions. So they are usually considered as a medium fidelity method. The fourth one is potential flow-based models. They are actually panel methods. Normally, they are implicit incompressible. It's an implicit incompressible method, but we can include the viscous effects with a boundary layer code and a free wake. Moreover, apart from the previous method, we can consider blade geometry by direct discretization. So in other words, we do a surface mesh of the blade, but that's it. We do not have to mesh the whole volume, just the blades. So this reduces pre-processing time significantly. It has incompressible flow assumptions, but there are compressible panel method as well, panel method codes. The problem is there is uncertainty in vortex core modeling, and at each shed of the turbines, the vortex filament interaction calculations gets more expensive and more expensive. So that's a problem. But there are some codes with parallelization, like this simulation was extracted from a GPU parallelized panel code. And what we have left is 5 and 6, actuator display surface and direct modeling. Both of them depend on Rand's LES calculations. So in the actuator disk-like surface, the blade is not represented directly. It's represented with an actuator force source. It could be an actuator disk, actuator line, or actuator surface. So in such a case, we do not need to discretize the blade. We do not have to put boundary layers. That's why the less pre-processing time is required. Apart from panel method, it requires volume mesh since we do runs LDS calculations. So such methods requires an accurate model. So of course, we do not directly model the blade, but we should put an accurate model instead of them. And also we have to feed this model with the accurate blade data. But still, this is the most popular one for wind farm analysis, for complex analysis, not for optimization or wind farm layout works, but to see the flow within a wind farm. Usually actuator disk line or surface methods are preferred usually. And the last one is the direct modeling. So we mesh each turbine individually, we put boundary layers, we model them as they are, and it requires high quality mesh with fine boundary layer representation. As you can imagine, it's extremely costly. It is almost impossible to do an optimization or similar application with such an approach. So this was the end of my introduction presentation. So thank you for your interest. If you have time, so I think we have plenty of time for Q&A. You can ask them from the Q&A session.
Okay, thank you, Ata, for this nice presentation. We have a few questions, I guess. I guess I missed the first one. Sorry. Did we answer that? I think it was from the previous. Okay, yeah. Could we provide the
question?
Okay, could we provide a wave angle through the model of offshore turbine in the model? Yes, we can input incident wave propagation heading direction in degree to the hydrodyne module. So wave angle, you mean not straight wave, but with an angled wave. Yeah, it's possible, right?
Yes.
Okay.
Yes, it's possible.
Thank you. Çalışma konusuna yeni dahil olmaya çalışan biri olarak benim açımdan çok verimli bir workshop oldu. Tüm sunum yapan hocalarımıza ve tüm emek ve düzenlemeleriniz için size ayrıca teşekkürler. Teşekkürler. Umarım faydalı olmuştur. Daha sonra da sorular sorabilirsiniz istediğiniz zaman, merak ettiğiniz veya takıldığınız her zaman bize sorabilirsiniz. Yardımcı olmaya çalışırız. Rüzgemi ziyarete bekleriz. For local some wake models, this is for you, Ata. How can we find local incoming velocity to a turbine without running the simulation? That's a good question. Actually, yeah, you can answer.
Yeah, so you can write a code to start from the most upstream one. So let's say that you shed wake from these upstream turbines, then check whether the next line is suffers from that wake. If not, again, you can shed them, and let's say that we come to the turbine, and this time we see the effects of the wake. Then you can just get the wake velocity up to here, apply the wake superposition methods, then continue with this ones, the turbine. You can go 4, 5, and so on.
Mm-hmm. So you add one by one.
Yeah, you can go in the flow direction. Take perpendicular lines and go one by one.
Okay. Okay, so I think in the next presentation we will see more detailed CFD simulations for the wind farms. But this is the engineering models that is widely used still for the estimations, wind farm power estimations or design or layout design
So they are still being used and people still try to improve the models. Yeah. Okay, I think we have another question about the wave direction. Putra, you mean, yeah. I mean, if you have a straight wave coming towards the turbine or at any angle, maybe it's aligned with the wind. Wind might be coming with an angle, also yaw condition. So they're all possible, yeah, from all any angles you can define. Or opposite direction, if you are asking, for example, is it, I mean, it may be possible, right? But usually, I guess the wave is aligned with the wind. I am assuming, is it correct?
Yes, true. Dr. Nilay, most of the time it's aligned actually.
So,
I mean, not inversely. Perhaps there are slight difference, but actually not coming from back, I guess. But we can also try any different scenarios. Actually, all of the degrees of freedoms are available, so it can also come from every directions.
So if the turbine is aligning itself with the wind, the rotor, at least the rotor is aligning with but the tower is not, maybe, right? So, or the platform, it's not possible to align if they are anchored with some direction, with some specific.
Yes,
so,
exactly.
Yeah, they have
The
some limitations, right, with the movement. Okay. Great.
By the way, I may add some clarification to Levent's question. I think my answer was not very clear. So as I talked earlier here, so we have the local blockage effect in CFD, but in wave models we do not. So let's say that over here we have still a uniform velocity until we see a turbine. So the wind turbine only affects the flow of the regions of its downstream. So in such a case, you know,
you need to improve the model.
Yeah, like in such a wave superposition model, you can, you know, discretize the flow in the flow direction. So you can, you know, calculate each perpendicular lines, points on perpendicular line. So for example, if we calculate this line here, so we know that there's only the turbine's waves over here will affect that. So if we go the second line, then, you know, we have the contribution, a new line, so you can then superpose them. We can go in this direction step by step.
Okay, and go to the next line with the actual superposed velocity inputs, right? Okay, thank you. Another question or comments? Açıklayıcı ve etkileyici sunumlarınız için çok teşekkür ederim. Konuya benim gibi yeni dahil olan kişiler için de çok faydalı bir seminer oldu. Saygılarımla teşekkürler. Başarılar diliyoruz. XYZ, okay, we will talk with you, I guess. Yeah. If it's not clear, we can discuss. You can chat with Putra, or we can try to clarify with the simulations with the wave direction. Thank you. Okay, these are, I guess, done. Q's question to add. Ata.
That's me.
Yes. Which model is most useful for the wind farm blockage effect? That's
I believe you
very
are.
Difficult question.
I think you mean this, you know, the interboundary layer or everything, right? Not as this local blockages. So until a few decades, this was not introduced in wake models, as I know. The only goal of the wake models was to, you know, get the just do directly the wake effects. But nowadays, as I know, the modern wake models try to include this farm blockage effects, but I know which one is better because, you know, normally when we see the research, although new models shows, you know, great accuracy, people still use older ones like over here we have this top head shape. They are still using many works, so that's why I did not encounter such a model there are new models, but I do not encounter them in applications, so that's why I don't know which one is more useful. But there are lots of review articles about this wake models. You can, you know, open literature and see that.
Mm-hmm. There are recent papers, as you said. Yeah. There are also experiments planned or wind farm measurements also used, and also the inflow free stream is not always very smooth. So there are other studies considering the inflow effects as well.
Also, there's yaw effect. So there are lots of variables. So, you know, the wind energy committee, you know, always puts top of the remaining parts. So probably there is a model recently published but not tested. But probably your question, the answer of your question is one of the models, but you know, I don't know personally.
Okay, thank you. Okay, so we have another question for Putra. May I use OpenFast to establish dynamic modeling of wind turbines?
Okay, so OpenFast is most of the time used for simulation purpose. And actually, if by that mean dynamic modeling means obtaining the performance and everything, then we can do that. Actually, so the modeling is done before simulations. So in fact, it's the input of OpenFast.
Mm-hmm. Okay, but is it coupled? I mean, you can do coupled dynamic motions, right? I mean,
yes,
as a result of the aerodynamic and hydrodynamic forces and moments, your turbine has a motion, resulting motion. So they are coupled, right?
Yes, it's true. Actually, Elastodan is accounted for all of that. Actually, that's why Elastodan is executed before everything else.
Okay. So they run in an order, probably in the code, all the models that you want to implement, or all the assumptions that you want to include. So when you select your input files accordingly, when you run the OpenFast, it will show you the effects. Yeah.
Yes, exactly. I hope this answered the questions.
Okay, thank you. So thank you, Ata, for the presentation, and thank you, Putra, again. So I think we have some time for the next presentation. We can wait until 4:10, 16:10. So if you have any questions, you can keep writing and we can answer again later on. Thank you. Thanks, everyone. Okay, hello everyone. So we are back with the last presentation. Maybe I can show here. Okay. So today's workshop's last presentation will be given by Hüseyin Can Önal. He is also a research assistant and PhD candidate at the Department of Aerospace Engineering in METU. And he will talk about wind farm CFD analysis by using OpenFOAM CFD software.
Okay, Hocam, can you hear me?
Yes, we can hear you. You can share your presentation now. Thank you.
Okay. I'll just share my screen.
Mm-hmm.
Okay, is it okay?
Yes, great. Thank you.
Okay, hello everyone. So I'm the last presenter in this nice seminar, and almost everything has been told about wind farms already. So there is not much left for me, but I will not try to bore you much. I'll try to be brief about the things that are already being spoken about, and I'll try to give you some new information if possible. So this is wind farm CFD analysis by using OpenFOAM. I will mostly talk about the wind farm CFD part and show you some very simplistic simulation with OpenFOAM at the end. So wind farm simulation. So what are the objectives and challenges? This is the first important thing, I guess. So the common objectives are, as most of you know, estimating the power output, right? And other than that, the aim can be to plan the layout, that is to design the layout or optimize the layout, where to put the wind turbines. Or purely you may be after observing the wake interactions, or you can be studying wind turbine dynamics, like the loads on the blades or fatigue of the blades or the tower, things like that, and many more things. But these are the most common objectives mostly. And wind farm simulations are actually quite challenging, and some of the reasons are the wide range of length and time scales, right? Because we have the millimeter scale, length scale on the blade surfaces, and this is the minimum length scale, all the way up to the kilometer scale of the flow over the field. So we have to resolve a large, very wide range of length and time scales at the same time. Other than that, the wind and weather is very chaotic in nature. So if you are trying to estimate the real power output of a wind farm, you have to capture most of this chaotic nature. And it is very difficult to capture all of that. Because as the name implies, it's chaotic. Even if you check the weather report or weather predictions, most of the time you come up with a completely different weather the day after, right? So other than that, the physics is also complex. Ali Ata also talked about that, the shear layer, the atmospheric boundary layer. The atmospheric stability is also another factor, such that if you check this graph here, from noon throughout the day, the behavior of the weather, behavior of the near surface flow changed dramatically. The atmospheric boundary layer becomes stable and unstable as the surface temperature changes throughout the day. That includes heat transfer and buoyancy. So these are the challenges you face when you try to simulate the wind farm. So to outline my presentation, the core components of a wind farm simulation, as you can see here, is I mainly divide them to two parts. The first one is the bulk flow over the terrain, and the second one is the wind turbine modeling. So in the first part, we will think of the wind farm without the wind turbines. We will just consider the wind flow over the terrain, right? And after that, you have to put the turbines into the game, and so that you can capture the power production of a wind farm. And lastly, I will talk about the capabilities of OpenFOAM very briefly. So bulk flow over the terrain includes turbulence modeling, boundary conditions of the far field, and boundary conditions of the terrain. So you know about turbulence modeling already. We can use LES, largely simulation, or Reynolds average Navier-Stokes equations. So other than that, we have to develop the mean flow over the terrain, considering the bulk flow, and this is a challenge on its own, right? So boundary conditions of far fields is the simulation going to be steady or unsteady, statistically speaking? So that changes your boundary conditions at the implementation of the boundary conditions. And about the terrain, are you simulating an offshore or onshore wind farm? Is it flat or a complex terrain? This also changes everything. For example, on a flat terrain, you can use cyclic boundary conditions, but on a complex terrain, you can't do that. So, you have to implement some roughness treatment. Things like that. About the wind turbine modeling, you have already listened in quite detail, but I'll talk about full blade geometry result mesh, power curve estimations, and actuator models. Okay, so let's start with the turbulence model. So we can use runs or LES, right? So runs is computationally cheaper, as you know. You can perform steady state simulations using runs, because with LES it's impossible. LES is inherently unsteady, and running an unsteady simulation is orders of magnitude more expensive than running a steady simulation. So you have to choose a suitable closure model if you are using runs. By the way, I'm assuming that you know the basics about runs and LES at this point. It can be an eddy viscosity model based closure model, or Reynolds stress model based closure model. So EVM is a much cheaper and economical approach, and it employs the linear hypothesis of Boussinesq, as you know. So we have the velocity gradient divided into strain and rotation parts, and we assume that the Reynolds stress, this turbulent stress tensor, is linearly proportional to the strain rate tensor, S. Right? So this assumption is actually good for isotropic turbulence. But when we're simulating a wind farm, especially in neutral atmospheric boundary layer region, and in the wake region also, the flow is strongly anisotropic. So this assumption fails. I mean, it fails to some degree. For example, in the standard K epsilon turbulence model, the turbulent viscosity is equal to a linear proportion of turbulent kinetic energy and dissipation, right? So if you keep this C mu constant here, if you remember the K epsilon turbulence model, it becomes very dissipative. The flow in the wake region, it is numerically dissipative. So you encounter an over-recovery of the wake. What I mean by over-recovery of the wake, in the wake region, you have less velocity, right? So wake, as the flow goes downstream, recovers its velocity. but using K epsilon, this happens very quickly, which doesn't agree with the experiments. So if you're using K epsilon, you have to bear that in mind. So what about improving them? So I'm going to show you briefly two turbulence models, two improvements to the K epsilon turbulence model, which considers the turbine wake specifically. So you can check this paper. In this approach, Kasmi and Mason added a source term to the dissipation equation in the rotor vicinity only. Okay, so if you imagine the epsilon equation in the Rans equation set, there is a C4 constant. So this C4 is not general and must be calibrated. So in this paper, the authors they have modified this constant to agree with the experimental results at the wake region. But nevertheless, they keep this C4 constant, okay? The good thing about this turbulence model is it agrees with the experiments well in a portion of the wake region, in the near wake, but it fails to capture it in the far wake. So there's some improvement, but not enough. I mean, we want a good agreement throughout the wake region, right? All the way down to the full dissipation. So another improvement after that turbulence model is from Van der Laan et al. So simply, they have developed a turbulence model called K epsilon FP. The idea is that it can handle anisotropic turbulence more successfully. So it is less dissipative for high shear regions and lowers the eddy viscosity downstream. By doing that, it can give a good wake development or wake breakdown throughout the whole wake region, as you can see it here. There's a quite improvement. The red line is the classic K epsilon, and this K epsilon FP is the model proposed in this paper. So you can see that it agrees with the measurements quite well, from 2.5 diameter downstream to 7.5 diameter downstream. So it's quite good. So if you're in the future, if you want to use a K epsilon model, you can consider this model. Okay, other than the EVM, eddy viscosity model, the other option which runs is, as you know, is the Reynolds stress model. So in this model, we look forward to estimate all of the components of this Reynolds stress tensor, right? Here, the challenge is boundary data for this Reynolds stress tensor is obtained from experiments, right? So you have to, the case you are simulating should be somehow similar to the experiments that gives you the boundary condition for that UJ Reynolds stress tensor. I mean, if you want to simulate the flow using RSM, you have to put the boundary conditions for these tensor elements, right? So these comes from an experiment. So you have to find a good experimental data to start with. So this is a challenge for that. And other than that, roughly computational cost is 2 times the standard K epsilon simulation. So you should also bear that in mind if you are using RSM. You get better results, but you have to perform more computational time. Okay, so what about LES? If you check the literature of wind turbine simulations, CFD simulations, you mostly come across with LES. Most people use LES. So to remember it briefly, in LES, large eddies are resolved and smaller eddies are modeled, right? And energy spectrum is a field variable here. So when you see this energy spectrum graph, it doesn't cover the whole domain, right? So it is different for each portion of the domain. Actually, each cell and its vicinity has a different energy spectrum graph. So if you can capture 80% of the total kinetic energy in the result part, it is considered to be a good LES, because there is no grid convergence for LES. You can refine your grid all the way down to the DNS, direct numerical simulation, but it's not feasible. So 80% resolution is enough. A good practice for simulating wind farms using LES is obtaining the integral length scale from runs beforehand. So you don't usually start right with the LES using LES. You're running runs beforehand, and using that field to initialize your LES simulation is a good idea for wind farm simulations. So subgrid length scale is usually the cube root of the cell volume. The thing about LES is there is no epsilon equation to be solved, right? There is no dissipation equation to be solved, and dissipation is a major challenge in wind farm simulations. So you have to resolve it. So a subgrid scale determines eddy breakdown and dissipation. You have to use a subgrid scale model, and standard Smedlensky or other dynamic models can be used for that, which I'm going to talk about in the following slides. So LES, it is higher fidelity but more expensive. If you are using LES, be ready to spend 3 order of magnitudes more computational time than runs. This is a very big difference, right? So unsteady simulation is required inherently. You can't run a steady simulation, and running an unsteady simulation takes much more time. Very sensitive to grid resolution. Your grid quality and the resolution of your grid must satisfy some certain criteria. And highly anisotropic. So Smedlensky subgrid scale model is the simplest subgrid scale model for LES. It resembles the eddy viscosity model in runs, but again, it is assumed to be the Smedlensky subgrid scale assumes isotropic turbulence nevertheless. So it may fail again. So you should have use dynamic subgrid scale models, right? Aerodynamic loadings are not sensitive to turbulence. So this is a common finding from a lot of the literature. The turbulence intensity or the turbulent behavior does not affect the first turbine, which faces a clean flow, but it dramatically affects the turbines after that. It dramatically affects the turbines which remain in the wake of another turbine. So this is really interesting and complex. And special treatment is needed to generate atmospheric turbulence. If you want to generate atmospheric turbulence, in runs, you can just play with K and epsilon values at the boundaries. But in LES, you can't do that because there is no K or epsilon value that you can directly manipulate. So you have to manipulate them through grid sizing, cell sizing, or additional models. So standard Smedlensky and in LES. I've already talked about it. SGS tensor is based on eddy viscosity model. Again, it assumes isotropy and it may fail in certain areas. Using Smedlensky subgrid scale model with LES, the model constant 0.17 is well determined for homogeneous isotropic turbulence with inertial subrange. But this is not the case for an atmospheric boundary layer flow. as you have seen beforehand in Ata's slides, atmospheric boundary layer is a shear layer. So depending on the stability of the boundary layer, stable or unstable or neutral, this CS value should be modified accordingly. You can't keep that constant. It is also too dissipative for inhomogeneous and anisotropic flows, as I've said. In strong shear, I mean, if the shear profile is really strong, then you need further case-dependent calibration. So it is not easy to just use a LES model and just putting in some constant numbers. You have to tweak them, or you have to use some other additional dynamic models. Okay, so these are quite theoretical. Maybe I should skip through these, but I want you to know that other than Smagorinsky, which if you are going to use LES, you will come up with the first thing. There are scale-dependent Lagrangian LES models. So the idea is to make that CS constant, this model constant, not a constant, but a variable which changes in space and with time, so that you can capture the resolved eddies and resolved turbulent dynamics more accurately. I'm not going to delve deep into these equations, but you should consider using one of these models. You can check this paper for further instructions. Okay. Okay, that's all with the turbulence models. So what about the boundary conditions? So if you have already simulated anything with using CFD, boundary conditions are very important. Actually, boundary conditions are the only thing that changes your solution, right? Because almost for every solution, you're almost solving the same equations: momentum, continuity, energy, etc. But the boundary conditions dictates what solution you get. So they are very, very important. Is it your simulation going to be statistically steady or unsteady in your wind farm simulation? It is very important because it decides which turbulence models you can use or which turbine models you can use and how are you going to use them. So this is very important. For example, if you check the figures here, so this is a statistically steady flow, right? Unidirectional. So the same flow is same throughout the domain. So let's consider that this blue rectangle is our flow solution domain. So unidirectional, constant unidirectional flow is the simplest one. So this is also a steady flow, but this is not unidirectional, let's say. So you can see that there are some inflow regions. For example, this, maybe I can draw. So this is an inflow region. This is an inflow region. But for example, what about this boundary? This boundary up to this point, this region is inflow. But if you can check here, this region can be an outflow. So boundary condition implementation becomes very, very complex. I mean, you have to treat these two regions separately. Okay, so we said that this is a steady state. But what about it is unsteady? So, for example, this region may be an outflow region at a certain time step, but after some time steps, this region can become an inflow. So you have to check each cell, each point individually throughout each time step to change their type, right? So this is also a complexity. So what can we talk about here? And what about LES, right? So how to generate inflow turbulence? Because inflow turbulence is very important such that it changes the wake dynamics. Remember from the slides, presentations before, if you have a turbulent flow, the wake recovers so much quicker. For example, if the inflow is not turbulent, your wake can recover in 6 diameters downstream. But if the inflow is turbulent, it may reduce to 3 diameters downstream for wake to recover itself. You have to capture them accurately to obtain a good power output estimation. Yes, that is what I'm talking about. You can see here that this is from another study. I didn't put the reference, sorry for that. But inflow turbulence has a dramatic effect on wake structure and wake recovery, and also accordingly wake-induced power losses. So your first turbine is here, right? Okay, so let's say your second turbine is here. So if you have the inflow turbulence in the second picture, this is turbulent inlet and this is uniform inlet. Please observe how the flow is dramatically different. So if this solid line is uniform inlet and this dashed line is turbulent inlet. Yes, so the velocity deficit is much more smaller in turbulent inlet. This means that if the inflow is turbulent, the downstream turbine should produce much more power, especially if you consider the cube, consider that the power production is proportional to the cube of the velocity, right? So inlet turbulence, very important. You should bear that in mind. Okay, so we said that inflow turbulence is very important, and if you are using runs, Reynolds average, Navier-Stokes equations, you can change the inflow turbulence by changing K and epsilon values because you have equations for those field variables. But what about LES? We don't have K, we don't have epsilon equation. We can't control K directly, right? So you have to use additional models, additional tricks to generate some sort of turbulent activity at the inflow, at the boundaries that can resemble a real life situation. So this is also not an easy task. There are some different approaches. So you can see 4 different graphs here. So the first one is white noise, okay? What is white noise? White noise is a method which is not very physical, but you randomly disturb the flow at the inflow and generate some sort of eddy motion, right? But for example, this is not good because it dissipates quickly. Actually, I've used that and see it with my own eyes. This is true. I mean, this is not physical. It is not recommended for wind farm simulations. You have other approaches also. And these approaches can be divided into 2 parts. This is a kind of advanced topic, but it is very interesting, so I want to talk about it. To generate turbulence, inlet turbulence, using when you are using LES, you have 2 options. The first one is synthetic models, and the second one is precursor models. So what are these? Synthetic models are less expensive, but they have lower fidelity. In synthetic models, you using tricks, you generate eddy motion yourself with, as I've said, using forces and stuff like that. Another thing is precursor methods. So what is precursor method? In the precursor method, you simulate the domain beforehand, before you carry out your actual simulation. You just develop the turbulent flow throughout the domain using cyclic boundary conditions, which I'm going to talk about in a minute. But I've talked about synthetic models. There are different approaches, but you have to be sure that it resembles physical, real physics, because it is not guaranteed. In a precursor simulation, it is almost guaranteed. You have higher fidelity. Okay, this slide shows the synthetic models, and this is about the precursor approach. So, what is a precursor approach? Let's say this is our domain, right? This is our domain. So this is the north direction, and this is east direction, and we want to simulate the wind flow here with LES, but we want turbulence. So, precursor atmospheric boundary layer simulation. You perform a simulation first with no turbines, only a flow, only a flow using cyclic boundary conditions. For example, in this direction, right? So this boundary and this boundary are cyclic, and using some special, adding some special terms to the momentum equation, and running it for, let's say, for 1 hour, real simulation time, you obtain a fully developed LES region like this one. And after that, you cut planes from this simulation, right? You get a plane cut, and get plane cuts at every time step, or within a certain interval of time steps. You extract these inflow boundary data planes, and then you can use these already turbulent boundaries to use your actual simulation. This simulation is completely independent from this simulation. In this simulation, you use these boundary cuts to obtain a turbulent inflow in your LES simulation with turbines present. Okay, so you develop the flow in an empty domain, get planar cuts, and use them in the main wind farm simulation. This is more physical, more expensive, and you can see in the literature that there is a greater adoption for this model. A major drawback is the periodicity requirement. So, if you remember, I told that boundary conditions, turbine models, turbulence model, terrain complexity, flat or complex terrain, these all affect each other. For example, if you want to use a precursor turbulence generation approach, your terrain should better be flat. If it is complex, if it is not flat, the periodicity, the cyclic boundary conditions will not work well. Stuff like that. I mean, you should consider what you want to obtain from your wind farm simulation, and what is your limitations, your computational power, and decide what are you going to use at the end. There are much more improvements to this model. For example, some researchers employ concurrent precursor simulations, which where this simulation and this simulation, they are performed simultaneously. So this avoids input-output operations dramatically. So this is also important because you are outputting a lot of planar cuts. Input-output operations takes a lot of time, and this is another drawback of the simulation type. It takes so much time and so much hard disk space. Okay, let's move on. Other than that, for example, up to this point, I've been talking about unidirectional wind flow, right? If you check here, what I've talked so far is this one, unidirectional wind flow. But what about it if it is unsteady? So what are we going to do? If it is unsteady and complex boundaries, this approach, I don't know how to perform this approach actually. You can't use that, I might say. I mean, there might be some approaches, but I don't know about them. So it becomes very difficult to use that. So what if your boundaries are time varying, like that? So if your boundaries change with time and you also want turbulent inlet, then you should use runs, for example, not LES, because it's difficult to obtain the turbulent inlets. Okay, time varying boundaries. Variables at the boundaries should vary in both time and space, right? So that means boundary condition type, which is Dirichlet, Newman, or a combination of both, should also vary in both time and space. And this becomes challenging in incompressible solutions, not compressible. I mean, choosing a compressible and incompressible solver also affects everything else, and also the boundary conditions. Okay, what am I talking about? Let's say we have a cylindrical domain, right? And boundaries are time varying. You can't know whether it is inflow or outflow at any time. It changes dynamically. So what are the boundary conditions in an incompressible flow solution? If you remember, at the inlet, U is Dirichlet. You directly give the value of U, for example, 10 meters per second. At the outlet for the velocity, you put zero gradient boundary condition, right? If you have a domain like that. At the inlet, U is Dirichlet. A fixed value is Dirichlet boundary condition in open form lingo. And at outflow, you put zero gradient. For pressure, you put zero gradient at inlet and zero at output. Dirichlet-Newman. So this becomes very challenging when the boundaries dynamically change, because at every cell, if you have cells at the boundaries like that, this cell should change from Newman to Dirichlet depending on the flux sign. If it is in flow, it changes. If it is outflow, it changes, right? You have to code these. You have to implement these into your code. Other than that, where do we get these values from, right? I mean, if this is our domain seen from the top, okay, we draw arrows like this, but where do these arrows come from? Where do I get my boundaries from? For this, I should briefly mention weather prediction models and weather prediction codes. For example, WRF. WRF stands for Weather Research and Forecast, and it is a solver by itself, other than OpenFOAM. It's a standalone solver. It just solves for weather forecast. Okay, it gets weather forecast data, and for a limited region, for example, this is global forecast data, and you want to solve for this portion of the United States, for example. You get this data, and WRF solver use the global forecast data as boundary conditions and initial condition for that region, and it solves the flow here, which then you can extract boundary conditions from WRF and use it as smaller scale boundary conditions in your OpenFOAM simulation, for example. I mean, these are quite advanced stuff, and I have limited time. I hope that I'm not going very fast, but to complete, I have to keep the pace. If you have any questions about this, if you don't understand, please write them. I will try to answer them at the end. Okay, let's move on. Okay, so we have talked about the lateral boundaries, about the inflow, outflow, lateral boundaries. So what about the terrain boundary? So flat terrain is idealized. It is used for testing. It is used for model adjustments, and it is used for offshore wind farm simulations. Most of the simulations you see in the literature are flat terrain. And complex terrain is mostly used for onshore wind farms. You have the mountains or forests and stuff like that, and the terrain shape, terrain geometry changes. Fitting the grid over the obstacles such as trees and buildings, is impractical, right? So you're simulating a 5-kilometer field. So 30-meter height buildings cannot be fitted into the grid. It increases your cell count dramatically. So instead of doing that, you represent them as roughness elements. So you implement them into the momentum equation as a term, and a roughness constant handles them. Just like if you are solving an airfoil and you can put a roughness on the airfoil, right? 0.3 microns or stuff like that. And it changes your transition point. If you can resemble this phenomena to that. But in the flow field, it is much higher. So using a wall function instead of resolving the boundary layer. You have to do that because otherwise the Reynolds number is very large in wind farm simulations, and using a wall function is almost a must-do. And you must put the first cell within the low-glow region. So impose the non-dimensional velocity profile. So, okay, you have maybe heard about the Monin-Obukov similarity theory. So the atmospheric boundary layer is something like that, right? So depending on the previous experiments and previous observations, the atmospheric boundary layer has a certain shape. So this shape can be obtained using wall functions and roughness treatments at the wall here, without using very dense grid resolution near the wall region. This Monin-Obukov similarity theory involves temperature flux, surface roughness, atmospheric stability, and buoyancy. These are all very important things to take into consideration if you want an accurate wind farm simulation. And Monin-Obukov similarity theory handles these up to a certain point. Using a wall stress model, our goal is to predict the total stress at the surface, viscous and subgrid stresses at the surface, which are, if you consider the deviatoric stress tensor, we want to estimate these components. And we do that by using resolved velocities and dimensionless friction velocity using LES. But nevertheless, these wall stress models are, again, mostly tested on flat terrains, and they can fail at complex terrains, especially if the terrain gradients are quite high. This approach can fail. Also bear that in mind. Okay, let's move on to wind turbine modeling very briefly. Again, Ata and Putra talked about these, but I will briefly mention them. So first I will talk about two extremes: free bleed geometry, resolved mesh, and power curve estimations. Okay, up to this point, we didn't talk about the wind turbines. We talked about the bulk flow, right? And now we put wind turbines or their representations into the flow field. So you can conventionally, you can put the wind turbine directly to the wind farm, as you see here, and generate a very good mesh around the blade, around the nacelle, around the tower. You can resolve the boundary layer all the way to y+1 and solve it. You can do that in theory, but it is very impractical because it skyrockets your cell count in your wind farm simulation. This is the highest fidelity you can get, okay, but it is computationally very expensive, especially as the turbine count increases, because if you want to simulate a full wind farm, you have many, many turbines, right? So if you apply this approach to every turbine, you can't do that. And also control implementation is difficult. Control is another thing. Turbines must face to the wind change their axis, change their yaw angle, change their RPM according to the wind speed, just as they do in real life. So this implementation is also difficult using this approach. You have to implement sliding mesh, stuff like that. So this is the most difficult one. So what is the other extreme? That is the power curve estimation. This is the simplest one. You get the, for example, this is your rotor. You get the velocity at the rotor center. You don't put any turbine at into the solution domain, and you just get the cube of velocity and multiply that with the power coefficient and directly get the power output of a turbine. But if you do that, you can't get the weight dynamics because you don't generate the weight physically. Maybe you can generate the weight with models that Ata have mentioned previously, but that is a model. I mean, it is not physical. You're just modeling it. But it is very simple. You don't have to implement anything additional. So what is the between? So in between of them, there are actuator models. In actuator models, very briefly, if you consider the solution domain, we represent the wind turbine as forces, okay? So we don't put any blade geometry, any geometry, any solid surfaces into the domain, but we represent this blade, for example, as a line that doesn't actually exist in the solution domain, but it has actuator points on it, right? So these actuator points here, let's say, these points impose a force to the solution domain. That force is added to the momentum equation, and this causes the flow to deflect as if there is an actual blade in the solution domain, right? So we are again using a trick here. Where do this force come from? How do we calculate this force? This force comes from the simple 2D airfoil theory. Lift, drag, the things you already know. So this you solve the flow in the domain. You get velocities at the actuator points. For example, let's say the flow is like that. So you have a velocity at this point. Using this velocity, you calculate the force that this actuator point would impose on the flow field. This force gets into the momentum equation and deflects the flow, changes the velocity. So using that new velocity, then you have to calculate the force again. So there is a velocity force coupling. Velocity changes force, force changes velocity. So you have to iterate on this coupling until that there are some convergence reached. So for example, in OpenFOAM, you can see it here. So it is an unsteady simulation, let's say. You start the time step, your actuator code calculates forces, you calculate velocity, you solve for P in an incompressible flow. P is uncoupled, as you know. You calculate the time step continuity errors, and then you have to iterate on velocity and force again. These are much more detailed. I'm not going to talk about it. We're running low on time. So this is an actuator model. And so actuator models also divide into two. There are actuator line models, where you represent each blade as single line, or an actuator disk model, where you distribute the force throughout the disk. Okay, so actuator line model is higher fidelity, but you have to perform an unsteady simulation for actuator line model, okay? Because these lines should actually rotate as the time step changes. So again, unsteady simulation, much more computation time. Your decision. If you want higher fidelity, if you are after higher fidelity, you should use this. But actuator disk is also okay. But for example, you can't accurately capture the tip vortices using an actuator disk. If you are after the wind vortices, you should use actuator line. So it depends on your final aim, right? Actuator disk also has sub-models, which are rotating actuator disk, or it can be a non-rotating actuator disk. Non-rotating actuator disk is even lower fidelity. There is only, here you can see, there is only a normal force, axial force. So if you are using a uniformly loaded actuator disk without rotation, you won't observe any flow rotation in the wake region, for example. For that, you should use rotating actuator disk or an actuator line model. Okay. If you have any further questions about this, please ask. So let's talk about OpenFOAM very briefly. I've explained a lot of things about general CFD for wind farm. So what if you are going to use OpenFOAM for that purpose? OpenFOAM has some useful features that are already available. The things I'm going to mention here also depends on the version, okay? For example, DFSEM does not exist in a certain version of OpenFOAM. So if you want to use DFSEM and if you don't find it in a certain version of OpenFOAM, bear that in mind. Find the version that includes DFSEM. I'm going to talk about it. Okay, so what about solvers? So OpenFOAM is a solver based on incompressible form of the Navier-Stokes equation. So I'm going to talk about incompressible solvers mainly. So you have simple form. It's steady, turbulent. Other than that, pimple form or piezo form. These are transient turbulent. These solves unsteady flow. So, for example, you can run simple form first to obtain a fully developed flow field. And after converging the solution, you can use the converged solution as the first time step of the unsteady pimple form solution, pimple form simulation. Because directly starting an unsteady simulation might be impossible because you have a terrain and you are trying to obtain the atmospheric boundary layer, right? So to obtain this atmospheric boundary layer, you have to use simple form first to get this, because in the first place, this flow is uniform at the boundaries. So in the middle region, this boundary shear layer can be obtained with steady solution. Other than that, buoyant business pimple form. For example, this is very similar to pimple form, but it employs the Boussinesq approximation for buoyancy, temperature-driven rho variation. I've mentioned the what do you call it? The atmospheric boundary layer stability, right? So if the surface is very hot and the weather is cold, you get an unstable region. To capture these accurately, you should use buoyant Boussinesq pimple form, for example. Pimple form can't do that. Okay, about turbulence. So you can have runs, K epsilon, K omega, or SST, they are standard. RSM also exists in OpenFOAM with two models, LRR and SSG. Also, LES is also usable with various subgrid scale models, Smagorinsky K equation, and other filtering approaches, anisotropic Laplace. If you are familiar with LES, these are important things, SGS and filtering. There are different models available. About boundary conditions, you have primitive Dirichlet-Newman and Robin boundary conditions in OpenFOAM. At the inlet, time varying uniform, so this is a boundary condition, for example. You can vary the boundaries. If this is our domain, you can change the boundary conditions with time, for example, using this. But this is uniform. For example, you can't put a logarithmic profile at the boundary using this. For example, for that, you have to code it yourself. Or you can use atmospheric boundary layer inlet velocity boundary condition type. Using that, you can make your inflow a logarithmic profile, but you can't change it with time. So this doesn't work with this simultaneously. You have to combine both of them manually if you want to use something like that. Actually, this is a part of my PhD thesis. There's a boundary condition called mapped. What is mapped? You can get a field data, planar field data, for example, a velocity data, and you can map it to the boundaries of this solution domain. Stuff like that, cyclic, periodic, or the synthetic eddy model that I've talked about previously. These are available in OpenFOAM. At the terrain, you can use nu-t k atmospheric rho wall function. I mean, these are advanced stuff. I'm not going to talk about them in detail. You can just go to the OpenFOAM webpage and see what these do. But this wall function gives you a logarithmic profile, develops a logarithmic profile within the solution domain based on the turbulent kinetic energy at the wall. And this is usable with runs only. But for LES, there is also another wall function that works in a similar manner. Other than that, one strength of OpenFOAM is its utilities. I mean, in OpenFOAM, you can directly use the dynamic mesh refinement, gradient-based dynamic mesh refinement. So in wind farm simulations, we are mostly interested in the wake region, right? So wake region is a fairly complex region. You have high gradients, large complex eddy motion, complex wake dynamics. So in the wake region, this gradient-based dynamic mesh refinement can be done immediately using the already coded features in OpenFOAM. Other than that, you can use sliding mesh, overset grid, and multiple reference frames. If you want to rotate the rotor region that Ata previously mentioned, these are also possible. Okay, lastly, we are almost out of time, so I will just mention SOFA. SOFA is developed by NREL, and it is a library for wind farm applications. What does it have? It implements the precursor atmospheric simulation that I mentioned before into OpenFOAM. In OpenFOAM, you don't have that, but SOFA has that. I mean, if you want precursor simulations, you can use SOFA. Also, it has custom wall stress models that works well for a wind farm simulation. Actuator line and disk models are also available in SOFA. Precursor I've talked about. And another thing is, if you remember Putra's presentation, he talked about OpenFast, right? Since NREL has developed both codes, you can couple OpenFast with SOFA. I mean, you can solve an actuator line in OpenFOAM, solving Navier-Stokes, and in real time, in simulation time, you can couple it with OpenFast so that you can get the dynamic loadings on the blades. For example, how do they deflect? How do they behave aeroelastically, right? So this is a neat feature. So this is the momentum equation SOFA solves. I'm not gonna go into that, but it includes Coriolis effects, which is an important thing, the deflection of wind flow due to Earth's rotation. It includes Coriolis effects, density normalized pressure gradients, buoyancy effects, actuator turbine forces. Everything is included into the momentum equation if you use SOFA. Okay, that's all.